Ladies and gentlemen, thank you very much for joining us for the 2020 Annual Symposium on ITER project and BA activities, fusion energy that creates a new future. I'll be acting as MC. I'm with the National Institute for Quantum and Radiological Science and Technology, QST. My name is Narita. My day job is research on nuclear fusion plasma transport. I ask for your cooperation. First, we'll have opening remarks on behalf of the organizer, Chairman of the Fusion Energy Forum of Japan, Dr. Naomasa Nakajima will deliver the opening remarks. Please. Thank you very much for taking time out of your busy schedules and coming despite the COVID pandemic. I think it was a lot of trouble to come here, but I very much appreciate this large audience. I serve as the chairman of the forum. My name is Nakajima. The Fusion Energy Forum of Japan, which is organizing this meeting, was established to support research and development toward the realization of fusion energy. And it is composed of experts from various fields, such as industry, research institutes, universities, and academic societies, who agree with the objectives of the forum. And also, we have participants from the general public who are participating voluntarily. Today, we hope that you'll have a chance to get a closer look at the recent status of the ITER project and BA activities, which are strongly driving fusion research and development in the world. So there will be lectures in this hall, and also we will have live telecasts from France as well. And in consideration of COVID-19, we have limited the number of seats available in this hall. But as a new challenge, we are conducting YouTube live streaming, simultaneous live streaming of this event, both in Japanese and English. So today's program is shown here. So we will have greetings from distinguished guests, followed by keynote lecture and special lecture. In terms of our guests, we have the following distinguished guests. Ms. Hinako Takahashi, State Minister of Education, Culture, Sports, Science and Technology, MEXT. And also we have Mr. Eisuke Mori, Chairman of the Parliamentarian League for Fusion Energy Promotion of the Liberal Democratic Party. Also, we have Mr. Hideo Ichikawa, Chairman of the Board of Showa Denko. He's Chairman of the Committee on Natural Resources and Energy at Keidanren, Japan's Business Federation. And also from Siemens, we have Chairman Mr. Kenichi Fujita. He's also Vice Chairman of the Environment, Resources and Energy Committee at the Keizai Doyukai, or the Japan Association of Corporate Executives. And then the keynote lecture that will be delivered by Dr. Bernard Bigot, Director General of ITER. We have a video message from him, and also we will be hearing live from him. He's at his home in France. And also we will hear from Dr. Eisuke Tada, Deputy Director General of ITER. He's here with us today. He'll be addressing you directly. And then we have Mr. Hideki Iwabuchi, Director for Research and Development Strategy at the MEXT, Ministry of Education, Culture, Sports, Science and Technology. He'll talk about Japan's fusion R&D policy. And then we have Deputy Director General Masaya Hanada of the Naka Fusion Institute of QST and Deputy Director General Shinichi Ishida of the Naka Fusion Institute of QST. They will report on the recent progress of a wide range of fusion-related activities in Japan, including BA activities, ITER support activities, fusion reactor research frontiers, and industrial applications. And also we have a special lecture by Dr. Ken Koyama, Senior Managing Director and Chief Researcher at the Institute of Energy Economics, Japan. He'll talk about the hot topic of COVID-19 pandemic and the international energy situation. I hope that you will stay until the end and get to know the results of the efforts being made toward practical application of fusion energy. Those are my brief opening remarks. Thank you very much.
Thank you very much, Dr. Nakajima. Moving on, we'd like to ask for the addresses by the guests who have come all the way out of their busy schedules. The first speaker is Ms. Hinako Takahashi, State Minister of Education, Culture, Sports, Science and Technology. I am Hinako Takahashi, State Minister of Education, Culture, Sports, Science and Technology, or MEXT. At the opening of annual symposium on the ITER project and BA activities 2020, I'd like to say a few words. In response to Prime Minister Suga's statement in his policy speech that Japan will realize carbon-neutral society by 2050, the government has been studying concrete measures. Nuclear fusion, which does not emit carbon dioxide, is an important energy source due to its self-sufficiency and safety features. For this reason, the government has positioned nuclear fusion as an innovative technology for a decarbonized society in the innovative environmental innovation strategy. The MEXT will continue to promote R&D for the early realization of nuclear fusion. The main themes of today's symposium, the ITER project and BA activities, are the two wheels to establish feasibility of fusion energy. In the ITER project, the assembly and installation ceremony was held in July this year, and messages were sent from each participating region. And participants from Japan, Mr. Hagiuda, Minister of Education, Culture, Sports, Science and Technology, delivered the message from the then Prime Minister Abe. Now that we have entered a new stage, it is important for each participant to play its role and further cooperate with each other. As for the BA activities, the assembly of the world's most advanced superconducting tokamak reactor, JT60SA, was completed in March this year, and we are steadily moving towards the first plasma. In April, the BA entered the next phase 2 to generate research results. I myself visited the Naka Fusion Institute last week and actually felt the strong level of progress of the BA activities. I would like to thank the fusion community for their steady efforts even during the pandemic of COVID-19. I understand that the Industry and Youth Exchange Meeting 2020 was held this morning. It is human resources, above all, that will support the long road ahead to the realization of nuclear fusion energy. Today, we have the participation of students and young researchers and engineers. I would like to ask you all to continue to be engaged with this dream project and to help shape the future. The MEXT will also continue to promote activities such as industry, academia, government collaboration, and human resources development. Thank you very much.
Thank you very much, State Minister Takahashi. Next, we'd like to call upon Mr. Eisuke Mori, Chairman of the Parliamentarian League for Fusion Energy Promotion. He's with the Liberal Democratic Party. He's a member of the House of Representatives. Please. Good afternoon. Thank you for the introduction. I'm with the LDP, and I head the LDP Parliamentarian League for Fusion Energy Promotion. My name is Mori. It's a great honor for me to be here today with all of you who are in the various fields related to the ITER project and BA activities. I'm quite thrilled to be here. And also, not all the seats are filled because of COVID, but we have a lot of people joining online, and probably we have more people joining this year than previous years. Now, in today's world, we need to solve the dual issue of energy and the global warming. In his policy speech to the Diet, Prime Minister Suga recently declared Japan's intention to reduce greenhouse gas emissions to net zero by 2050. In other words, to achieve a carbon-neutral, decarbonized society. Nuclear fusion, which is like creating the sun on Earth, produces no greenhouse gases in the power generation process, and its fuel is derived from the ocean. It's the ultimate energy that will fundamentally solve energy and environmental problems, as well as geopolitical problems concerning resources. Japan, as a science and technology innovation-based nation, needs to make a national effort to realize this and lead the world. In November this year, our Parliamentary League passed a resolution requesting the government to appropriately position nuclear fusion in the sixth Basic Energy Plan in order to realize a decarbonized society. The Liberal Democratic Party will continue to promote fusion energy and provide the backup or the support to the government. The most important project for the realization of fusion energy will be the ITER project and the BA activities, which are the themes for today's meeting. Japan has been leading the project from the beginning. I'd like to take this opportunity to pay my respect to all who have made great efforts to date. The ITER project is a symbolic international project promoted by the world's seven parties, and it must be made successful both technically and politically. Dealing with cutting-edge technology, I understand there were many issues that needed to be overcome. But under the leadership of Director General Bigo and Deputy Director General Dr. Eisuke Tada from Japan, understand that many reforms have been carried out. At the meeting of our Parliamentary League in July, Dr. Tada gave a lecture on the start of fusion machine assembly toward first plasma in 2025. I am very happy to hear that the construction work is steadily underway toward first plasma in 2025. I'm very encouraged by that report. The BA activities hosted by Japan are progressing smoothly in Rokkasho Village, Aomori Prefecture, and Naka City, Ibaraki Prefecture, thanks to the international cooperation between Japan and Europe and the active support of the local communities. I had the chance to visit the Naka Fusion Institute. At that time, JT60SA was under construction. I've been informed that it was completed in March this year, and that steady progress is being made toward first plasma. When first plasma is achieved, I would like to celebrate with my colleagues in the Diet in a big way. Today, we are joined by many people from industry, some online, and at the Fusion Parliamentary League meeting held in November, Toshiba gave a lecture on their efforts in nuclear fusion. And I was very impressed to hear that superconducting technology and processing technology obtained through nuclear fusion research being used in medical devices and semiconductor manufacturing equipment, enhancing the competitiveness of industry. Cooperation amongst the industry, academia, and the government will become even more important in nuclear fusion. I ask the industry people to take even more deeper interest in nuclear fusion. The ITER project and the BA activities are long-term projects. However, I believe that the project will be successful if all the parties concerned work together. I assure you that we, the League of Parliamentarians for Fusion Energy, will work with the government to provide you strong support toward realizing fusion energy as soon as possible. Lastly, I'd like to express my gratitude to Dr. Nakajima and all the members of the Fusion Energy Forum Japan, as well as to all those who worked so hard to organize this meeting. I hope that this symposium will be a milestone in further promoting and driving fusion energy research. Thank you very much.
Thank you very much, Chairman Mori. Next, we'd like to invite Mr. Hideo Ichikawa, Chairman, Committee on Resources and Energy, Nippon Keidanren, and Director and Showa Denko, Chairman of Board of Directors. Please take the floor. Thank you very much for your introduction. I am Ichikawa of Showa Denko, Chairman of the Resource and Energy Committee of the Keidanren, the Japan Federation of Economic Organizations. I'd like to express my heartfelt congratulations on the Symposium 2020 on the ITER BA activities being held this year again, despite severe restriction of social and economic activities due to COVID-19. I would like to say a few words from the standpoint of the Japanese business community. As you know, against the background of the recent increase in extreme weather events, a sense of crisis about the climate change is increasing more than ever, both in Japan and overseas. In our country, Prime Minister Suga declared in October that Japan will become carbon neutral by 2050, and various studies have been accelerated to achieve this goal. Needless to say, carbon neutral in 2050 is an extremely challenging goal. To achieve this goal, it is essential to pursue all kinds of options and create innovation that is not bound by existing technologies. From this perspective, in June this year, prior to Prime Minister Suga's declaration, Keidanren launched a new project called Challenge Zero to encourage member companies to take on the challenge of innovation for the even earlier realization of a decarbonized society. Keidanren continues to be committed to 2050 carbon neutral goal, determined to work toward the realization of virtuous economic and environmental cycles. Now, I believe that nuclear fusion is a promising option that the entire country should focus on. Needless to say, nuclear fusion is a technology that has no fear of depletion of resources, especially for Japan, which is an island nation, because deuterium and lithium, the raw material for tritium, is abundant in seawater. In addition, there is no CO2 emission during operation, and it is an energy source that can achieve both a long-term stable supply of energy and overcoming environmental problems. We expect that the practical application of this technology in the future will greatly contribute to solving global energy problems and climate change. As for the ITER project, which plays an important role in the realization of nuclear fusion energy, the assembly of the main body of the facility started in July this year, and I understand that it is making steady progress. We'd like to express our sincere gratitude to all concerned for their efforts and ask them to continue to steadily proceed with the process toward the commencement of operation. I understand that BA, the broader approach activities, are extremely important for the future implementation of nuclear fusion in society, including support for the ITER project and research and development for the realization of demo nuclear fusion reactor. In addition, I understand that the facilities related to BA activities such as Rokkasho Fusion Institute and the satellite Tokamak at the Naka Fusion Institute and the satellite Tokamak at the Naka Fusion Institute have become centers for training young researchers from around the world. I hope that the government will provide continuous support so that a younger generation can devote themselves to the development of nuclear fusion technology with dreams and hopes. Fusion has been called the energy of the future. But thanks to the efforts of the people concerned, we are making steady progress toward the start of operation of ITER in 2025. We believe it is important to inform society more clearly about the feasibility and usefulness of nuclear fusion, including these facts. Finally, I would like to conclude my brief remarks by wishing that today's briefing session will be an opportunity to make further progress in fusion research and development. Thank you very much for your attention.
Thank you very much, Mr. Ichikawa. Next, we have the Vice Chairman of the Environment and Natural Resources and Energy Committee of Keizai-do Yukai. He's also Chairman of Siemens. We have Mr. Kenichi Fujita, please. Good afternoon, ladies and gentlemen. Thank you for the introduction. I'm with the Keizai-do Yukai. I serve as Vice Chairman of the Environment, Natural Resources and Energy Committee of Keizai-do Yukai. And so this is the symposium on the ITER project and BA activities. I'd like to say a few words on this occasion. First, Dr. Bigo, Director General, and Dr. Tada, Deputy Director General of the ITER organization, and all those who are engaged in various broader approach BA activities in Karadash, Naka City, Ibaraki Prefecture, and the Rokkasho village. I want to congratulate you all on the start of full-scale construction and the transition to the integrated testing phase. So, two things I want to say. First, Keizai-do Yukai. Well, it has the Committee on Environment, Resources, and Energy. And last year, this committee had the opportunity to visit the ITER site. So I want to share with you what was our impression at the time of the visit. And also, I'd like to talk about what we want to do going forward. First, our first encounter with ITER was quite impressive. In some ways, it was shocking. I mean, before going, the members of the Committee on Environment, Resources, and Energy, which has a lot of industry experts as members, we got a briefing to learn about the technology and the nuclear fusion and the facilities, we really didn't have a realistic view or feel of what it was, even after the briefing. And to be honest, the average business person's or the average citizen's perception of fusion technology is that of a science fiction movie or animation, or it's something that's akin to astrophysics. However, about 1 year ago, we had the opportunity to visit, and our perception was completely changed. What I mean is that, well, we visited, and it was Cadarache, the center of French nuclear research. And in this plains, we drove by car, and suddenly we saw this huge next-generation energy facility. At that time, it was just the buildings, but it was quite impactful, nevertheless, to see all those buildings. And we got a very detailed explanation about the technology. We learned how innovative it was. We looked at the tokamak building and polyoidal coil manufacturing site. They provided us access to all of those sites. And, well, I'm with Siemens, a major energy player in Germany, made most of the power generation facilities in Germany. But in the private sector, we would never disclose all of these things. That was my impression. And they were so open to us, and we're very thankful for that. And we were able to see the innovativeness of the technology. We were able to look at the state of the art facilities. Was quite stimulating, very exciting. And I have to marvel at their effort, because it's a huge project spanning 7 countries and regions, and they were quite open to us, and I can understand how difficult it would be to manage such a huge project. It's huge and it's cross-border. I know how difficult that must be. So they had excellent management skills, and each person, I'm sure, has faced many difficulties, but they've overcome that, and I was quite impressed. So after returning to Japan, we also visited the International Fusion Energy Research Center in Rokkasho in Aomori Prefecture, and we were able to further enhance our understanding about the nuclear fusion energy technology. And as an economic organization, I'd like to talk about our expectations for nuclear fusion. So that's the second part of my talk. We have a long way to go. However, I feel that it's no longer necessary to call nuclear fusion technology a dream technology. The current energy and the power generation industries are faced with various issues, including zero emissions, and they have to focus on efficiency, high power output, environmental impact, fuel recycling, and cost. So they have all these dilemmas in this industry. So someone has to bring about breakthroughs. Fusion technology is no longer a dream, it's real. And it's something that we have to make real, is how we feel about this. And all of those involved in this technology and the industry and the government to provide support, they have to have that shared mission. And from the private sector perspective, we need to participate, support, and cooperate more from the private sector, so that fusion technology can be established as a business, to give reality to fusion technology as a business. That is what we need to work on, and I think further public communication is also essential. And finally, I hope for the future progress of ITER and BA, and for the understanding and support from the business community. Thank you very much. Mr. Fujita, thank you so much. So, in addition to the distinguished guests from whom we just heard, we have also participation from many other distinguished guests. Let me introduce some of them. A member of House of Representatives, Mr. Satoshi Asano. Thank you. Member of House of Councilors, Mr. Masaaki Akaike. Excuse me. Thank you. Member of House Representatives, Mr. Shuji Kira. Thank you. Member of House of Representatives, Mr. Mitsu Shimojo. He's represented by his secretary. Thank you. Member of House of Representatives, Mr. Akinori Eto, and his secretary is here on his behalf. From Rokkasho village of Aomori Prefecture, we have the mayor, Mr. Mamoru Toda. And also, we have received many congratulatory telegrams. Because of time, we cannot list them all, but let me share with you the names of some of the names of those who sent telegrams. Ms. Kuniko Inoguchi, member of House of Councilors. Mr. Yasufumi Tanahashi, member of House of Representatives. Mr. Hiroaki Kadoyama, also from the House of Representatives. And Mr. Jun Matsumoto, also House of Representatives member. Thank you so much to all who sent us telegrams. Let us now move on to the keynote lecture and the special lectures.
First, we'd like to ask the Director General Bernal Bigot, ITER organization, to report on the status. Generally, we ask him to participate in this kind of symposium live from the ITER site, but today we have the connection with his home, so he will speak about the status and the progress of ITER construction. And then this is recorded. And then after that, we have a live participation from the Director General Bigot. And then after that, we will listen to the report by Dr. Eisuke Tada, Deputy Director General of ITER. Without any further ado, let's take a look at the video message from Director General Bigot.
The new annual symposium of FEG in Tokyo. I am very pleased to have the opportunity to inform you about the latest progress the ITER project has experienced during the last 12 months. Indeed, we are always committed to open the way to a new energy future with hydrogen fusion, as you know, and so it's my pleasure to share with you the latest information. This year we have worked very hardly, and I am pleased to say that according to the stringent metrics that measure project performance, we are over 71% of the total construction from work scope through first plasma, which is still expected to be delivered by end of 2025. As you see on the construction side, many building and equipment has been installed, and we are really preparing ourselves in order to start with first plasma and later on to go on until the full fusion power by 2035. 6 years of steady progress indeed since I took office nearly. As you see, the comparison on the work site in November 2014 and the one in November 2020 is quite spectacular. We are now more than 70% of the installation civil works completed. We are working according to a revised construction strategy, fully adapted. And as you see, the black dot demonstrates what already has been achieved. And indeed, we are pleased to receive already some of the major tokamak components. And we will install all of them when they will arrive on site in 2021, 2022, in such a way that we will be able to close what we call the cryostat in 2024 and be able to start first plasma at the end of 2025. And as usual, we are considering the stage approach to the deuterium tritium plasma with full fusion power to be delivered by 2035, with some real physical experiment starting by early 2029 and for 18 months before we could install some complementary heating system. This year, we face a very challenging time with the pandemic of the COVID-19. Its impact not only the ITER site, but it impacts also many of the ITER members. And currently, we are still fighting against these pandemics, even if there is some hope with the vaccine coming in. We have tried to maintain all critical activities to ensure also personal health and safety. And I am pleased to say that we have been quite successful. We don't experience large infection on the work site, no cluster, no development. It was mainly on personal activities that if some people have been infected, we consider they could recover properly. I would like to speak about some recent progress. First, about the tokamak complex. As you notice, the tokamak complex now is quite impressively completed, with the tokamak just now ready for welcoming some of the major equipment. And indeed, in March 2020, we have been able to make access of the crane from assembling hall to the tokamak building. It was quite an important milestone, which opens the way to install indeed the base of the cryostat, a large piece, 1,250 tons, nearly 30-meter diameters. It has been lifted off, moved away from the assembling hall to the tokamak pit, and properly assembled. And once it has been done very precisely, we have been also able, by the end of August, to lower the cryostat lower cylinder in the pit and insert it very precisely, fitting with the base. And now on, we are welding the two pieces, the lower cylinder to the base, and I could tell you it's quite impressive to see how well they are proceeding, including the non-destructive leak test successfully, and it will last a few months still to cover all the welding material properly without any risk of leak. Indeed, the cryostat lowering in the pit has been the first step of very impressive progress associated to massive arrival of many equipment. As you see, the first one was in April from Europe, the coils, the TF number 9, but April also was the first coil coming from Japan, very impressive. We received another one in July, and so we are very pleased of the success of this transfer, which has been fully successful. We also received the vacuum vessel number 6 in July, as you see, and more coils are coming. The TF11 will arrive in September, and the TF number 5 from Europe also will arrive on the ITER site by mid-December. So really we are moving according to expectation. And now we are ready for first pre-assembly. As you see, we have the vacuum vessel on site. We have the two Japanese coils, TF12 and TF13, which are now pre-assembled. And we have also the vacuum vessel thermal shielding from Korea. And we qualify the system in order to be able to assemble all these components, the famous SS assembling tool, which is now really prepared. Beyond this impressive progress for the tokamak assembly, we are also progressing quite well with the balance of plant. And as you see, for example, we are installing cryoline in the tokamak building. There will be nearly 5.5 kilometers of cryoline, which will be cooled down at the minus 270 degrees, as you know. And you see that in the cryogenic plant, the cold box and a lot of cryogenic termination cold box equipment are on their way in order we are able to commission this equipment by mid-2021. Electrical network also, impressive progress. As you see, the complexity of this installation in order to secure the power to start and launch the plasma. All this equipment came from the various ITER members. They have been assembled. As you know, we got a connection to the French grid early 2019, allowing us to be able to check this installation performance. Electrical conversion is also a key equipment, and you see here all the bus bar, which will be able to transport the 70 kiloamperes, and this equipment are aluminum bars, which will be cooled by water, and you see how impressive it is indeed. Very big success, not only in the conversion building, but also in the tokamak. Heat rejection system is also a critical equipment for operating the tokamak, and you see great progress during the year 2020. The cooling water system is now ready to remove up to 1.2 gigawatt of heat, and all the leak tests was successfully performed on the basin recently. As you know, many manufacturing is going on with this special sharing which has been agreed when the ITER members signed the ITER agreement in 2006. And I just want to show you some progress. For example, here are the progress on the site with this specific colloidal field coil. And indeed, we have been very pleased to receive the PF6, number 6 from China and Europe, and they are performing very well indeed. But Japan has made also great contribution in 2020. As you see, for example, we have celebrated the arrival of the TF coil number 12 from Japan on April 2020, as I mentioned. And we are knowing also that there is a good progress in many workshops in Japan. But not only the coils Japan is providing, spectacular progress also on some very innovative high technology equipment. For example, the contribution of the 1 megavolt power supply for the neutral beam test facility, which is under preparation in Italy. It has been installed and absolutely secure to perform according to expectation. And also the famous gyrotron, which are supposed to feed in the plasma. And Japan has already pictured 4 of these 6 gyrotrons which have been delivered so far and qualified. But also some other contributors, for example, China with the feeders, India with the last segment of the lid top of the cryostat, and also Europe progressing with their delivery of the vacuum vessel sectors. They are in charge of 5 of them, and you see completion range from 65 to 81%. Korea has also to deliver still 3 vacuum vessel sectors, and you see the completion rate is even higher, up to 95%, and we expect that we will receive them on schedule. Russia is performed quite well with the polyol coil 1 manufacturing, entering in the final stage of fabrication, and the US is still always going on in order to provide the central solenoid module from the US. So I hope I share with you the real progress we have made during the year 2020, despite difficult situation associated to the COVID, which impacted, for example, the supply chain, also the capacity for traveling to some engineers and technicians. But we have been very strongly committed, and I am very grateful to all we contribute in such a way we keep the project on schedule and performance. And as you see here, we see the moon just looking at us, and we hope very soon we will be also the sun, demonstrating that we are mastering its technologies. Thank you very much.
ITER 計画の建設状況について、ビゴ機構長からビデオメッセージをご覧いただきました。それではご自宅のビゴ機構長からビデオメッセージをいただきます。現地フランスは朝6時です。ビゴ機構長、おはようございます。
Early morning at 6 o'clock.
よろしくお願いします。
Dr. Bigo, good morning. Thank you very much.
Good morning to all. It's really my pleasure from France to participate to this meeting. So ministers, honorable members of the houses, dear friends, including Tada-san, I know is with you. It's my real pleasure to speak to you after the very recent presentation you listened. And as you know, in the past, you kindly also invited me, and I was speaking with Tada-san from the ITER side. This year, due to the pandemic, we have closed the site a little bit earlier, before the holiday Christmas, because due to the pandemic during the summer, many of our staff has not been able to visit their family. And so we want to take care of them, and we invite them to take a few days more in order to be able to travel safely. So it is my real pleasure to join you now. As you know, this year, 2020, has been extremely challenging for all ITER members indeed. At the 2020 Fusion Energy Forum of Japan, 1 year ago, no one could have predicted the difficulty of the year ahead. As with all the ITER members, indeed, Japan has been a close partner, reliable and responsible for a significant part of the ITER project progress in 2020, despite the difficulties. Indeed, these years started in January 2020 with the celebration of the completion of the toroidal field coil 12, and it continues all through the years. Indeed, it was my pleasure to participate to the celebration, and it is a great achievement that Japan has been able to complete the first coil. This coil is now on site, very high quality. It is now properly completed with a few further equipment and ready to be assembled with the vacuum vessel sector number 6, as you saw on the presentation. The entire world, indeed, was tested this year. Private sectors, public sectors in every organization. ITER was indeed an example of success. 25 countries working together, literally hand in hand, toward a common goal for the betterment of humankind, and facing the pandemic, preserving the critical activities in such a way that we keep on schedule and cost in order to achieve hydrogen fusion before 2025, first plasma, and later on 2035, full fusion power. It was remarkable indeed to hear MEX Minister Hagiuda Ikoichi on 28 July with all the other head of state of the 6 ITER members beyond Japan, informing the ITER community that Japan has made fusion energy an integral part of its national progressive environment innovation strategy as an innovative technology that will lead to a carbon-free society. Today, many speakers also repeat how important is this commitment. A few moments later, it was also emotional to hear former Prime Minister Abe Shinzo's words referring to ITER as, I believe, disruptive innovation will play a key role in addressing global issues, including climate change, and realizing a sustainable carbon-free society. More and more, the public opinion, the decision maker in the world, realize that the current energy supply worldwide is not sustainable, and we need large innovation in order to cope with the challenge to replace, to substitute to the fossil fuel. And I am very pleased that Japan is a leading role in order to develop this technology, including with the GT60, which has been developed, and we have great hope that next year in 2021, first plasma will clearly demonstrate the capacity of Japan to support these fusion technologies. We cannot predict what 2021 holds, but the severe testing of 2020 has proven the reliability of the partnership we have with Japan and with all the ITER members. This gives us confidence as we look to the year ahead. So thank you very much for your kind attention, wishing you a happy New Year's, and we hope pandemics will be over and we will welcome you on the ITER side just to see firsthand how large is the progress. Indeed, these years, we expect to receive many other tokamak components and be ready for assembling them. And now, for example, a new coil has been completed in Japan and is on his way to be shipped, and we will welcome her, these coils very early next year, and more is to come. So thank you again for your kind attention, and I wish you all the best.
Dr. Bigo, thank you very much for joining us so early in the morning. Next, we have the Deputy Director General, Dr. Eisuke Tada, to give us a report. Dr. Tada, please. This is Tada from the ITER organization. We just heard from the Director General of the ITER organization talking about the progress of the ITER project. And despite the difficult situation of COVID-19, with your support, we were able to make steady progress in the project. So I'd like to thank you all for your support. So I'd like to talk about the ITER tokamak construction preparation status. At the construction site, you have all these buildings and plant facilities that are being built, and the various equipment that have been built by various members are being now put in place or arriving at the site. And so there was a celebration in July to commemorate the start of the assembly of the tokamak, attended by world leaders. President Macron of France gave us the opening speech. And this assembly ceremony, this was reported in 101 countries in 41 languages. And news related to nuclear fusion actually is increasing these several years. We want to maintain this momentum and further develop and produce results. We think that is quite important. At the ceremony, we received congratulatory speeches from the leaders of various members, as was mentioned by the Director General. We had the message from the then Prime Minister Abe, which was introduced by next Minister Hagiuda. The message emphasized the importance of nuclear fusion as energy policy and its future potential, including spillover effects. We also had Chancellor Merkel, President Xi Jinping, Prime Minister Modi, President Moon Jae-in, President Putin, and other leaders who gave remarks. And all of us at the ITER organization reaffirmed our commitment to move forward with this project with even more vigor. So about the tokamak assembly, so we have the three buildings, the loading building, assembly building, and the tokamak building. So at the loading building, the equipment is brought in, it's cleaned and washed. And in the assembly building, there are the assembly tools. And they are built into sector structures. And then that is carried by the overhead crane that can carry 1,500 tons. That's carried into the tokamak building and installed into the tokamak pit. So that's the overall flow. In more concrete terms, well, the equipment is very large, and so it's transported in horizontal position. It's cleaned in the loading building, then carried to the assembly building. And then there's this upending tool, and the equipment is changed from the horizontal to the vertical position. Then the overhead crane carries that and sets it into the assembly tool called SSAT. And then the 40 degrees sector structure is built. And so it has a vacuum chamber and 2 TF coils. And so it's a heat shield. And the sectors that have been built, carried by crane to the tokamak building and installed in the tokamak pit. So we repeat that process. And then with that, we're able to have the 660-degree tokamak assembly. So the first equipment has already arrived on site, as Dr. Bigo mentioned. So in more concrete terms, so the 40-degree sector, vacuum vessel sector, and the heat shield built in Korea, and the two TF coils, 12 and 13, built in Japan. They have arrived, and using the SS80 tool, they are made into a sector structure 40 degrees. And preparation work for the assembly is now being conducted on site. So the toroidal coils that have already arrived, well, the preparation for assembly is ongoing, and reference surface and interconnecting surface are being inspected, and various measurement equipment and cooling pipes are now being installed. In the assembly building, various preparation work is ongoing. 2 sets of the SS80 tools are available in the assembly building. This is the photo of that from the front. There is this white pillar in the middle, and the vacuum vessel sector is fixed. And this black part, well, the TF coil is set there in those wings. And then wing is rotated toward the center, and the vacuum vessel sector and the coils are joined together into a sector structure. So that's how it works. So the vacuum vessel sector, it's already carried to the assembly sector. And various measurement devices are being installed. As soon as that is completed, the appending tool will be used to make it into a vertical position, and then will be assembled. So in order to carry out this assembly operations in an efficient manner, we've reorganized the ITER organization in January. We now have 4 domains, and the construction domain is responsible for the assembly, also the engineering domain as well. Construction domain is responsible for the fabrication and assembly of the equipment necessary to achieve first plasma. And they also do coordination and management of the construction work. Engineering domain has the Central Integration Office, which is responsible for the design and technical integration of the tokamak components and the entire plant, and then the engineering design, which is responsible for fabrication, installation, and assembly of the components after first plasma. So we have 983 people. Japanese account for only 3.7%, still a low level. However, with the cooperation of MEXT and QST, the Japan Domestic Agency, and the industry, last year we saw some increases in the Japanese staff. We like to continue this trend and further increase the number of Japanese staff. So we like to continue our lobbying, and we also like to enhance the visibility of our results to promote the increase in the Japanese staff. The total number of Japanese staff is small, but in the new organization, the core positions of the head of the Central Integration Office and the Construction Management Office and the Chief Strategy Officer are occupied by Japanese. And so Japanese are playing central role in promoting ITER construction. And this is highly appreciated by Director General Dr. Bigot, and he has instructed me to actively increase the number of Japanese staff. So I'd like to take this opportunity to ask for your continued support and cooperation. And based on the progress of ITER and JT60SA, there's a renewed attention on nuclear fusion. In the U.S., a Fusion Industry Association has been established, and the Department of Energy has established a public-private partnership program. In the UK, the STEP program has started, And engineering contracts for demo reactors have been signed with several private companies. And so we have JT60SA progress, and there's a progress in other members as well. And in the ITER project, strategic alliances with global IT companies are being considered. And already, a comprehensive collaboration agreement has been signed with the NTT Holding Company so that the latest IT technologies can be applied in nuclear fusion. The start of the ITER assembly is a big step forward in increasing the certainty of the demonstration of fusion energy, and the future potential of this advanced technology makes it highly likely that it will become a huge industry, and so therefore each country is increasing the speed of development. So I believe it's time for Japan to move forward with the demo project in a concrete manner based on ITER and JT60SA progress. As Dr. Bigo also said, I'd like to invite you all to visit the construction site and actually feel the progress of the construction. And with that request, I would like to conclude my presentation. Thank you for your attention.
Thank you very much, Dr. Tada. Thank you. Next, we'd like to invite Mr. Hideki Iwabuchi, Director for Research and Development Strategy, MEXT, to speak about fusion research and development policy in Japan. Mr. Iwabuchi, the floor is yours. Thank you for your introduction. My name is Iwabuchi. I am responsible for nuclear fusion. I'd like to go straight into my presentation. I'd like to speak about the research and development policy on fusion energy in Japan. There are three major things that I'd like to speak about: the policy positioning of nuclear fusion, progress in fusion research and development, and status of studies for demo. So these are the three topics that we often talk about in Japan. Actually, about the second item, the next speaker will cover this, so I'd like to skip this. So I will focus more on the item number 1 and 3. I'm sure you are all familiar with this. Here we talk about the nuclear fusion, and this is the topic about the ITER, VA. So we focus very much on tokamak, but looking at the entire nuclear fusion, we have to think about long-term alternatives or diversity, and we have to consider various the topics to be covered in the R&D, including the helical type, and the laser beam for the magnetic field confinement. These are the kind of things that we take up in the scientific field. And here, we talk about the stage approach toward fusion energy. So I always use this sheet of paper or this slide in order to show what is taking place in Japan. And at this point, we can say that we are in the second phase. So we are now looking at the feasibility for the science and the technology. And there are 6 in ITER. And also at the Naka in Ibaraki, we have the research institute. And then we'd like to move on to the next phase, which is demo, and also the feasibility studies for the technology and the economy. So these are the things that we aim for demo. This will be done in ITER. So we will make the final decision looking at the final outcome of ITER 2025 and onward. So this will be something that would take place in the year 2030. So as was mentioned, the scientific research is important. So on top of the tokamak, we will also cover the 2 things, which is the helical type and the laser type. I'm sure you are all familiar with this. Then about the kind of the positioning of fusion research as an important national policy, allow me to say some things. I think you can go back to the presentation of the Chairman Mori. So the sixth Science and Technology Basic Plan would have to be taking a look at the fusion energy. This has been the proposal made by the organization. So please take a look at the current fifth Science and Technology Basic Plan, and also one more thing, which is the fifth Basic Energy Plan. And they are both of them looking at the nuclear energy as an important pillar. And at this moment, we are in the process of coming up with the sixth plan and the sixth strategy. And we will focus on them as well. And this is the slide I skip. And then I'd like to speak about what was mentioned by Prime Minister Suga. The most important is the first policy speech to the Diet by the Prime Minister Suga. And on the 26th of October, this has been widely covered in the entire nation. And he said that Japan will realize the carbon neutral society by the year 2050. So again, this is considered to be the carbon neutrality declaration of Japan. This is the objective that should be realized. In what way are we able to do that? So this is a major challenge that we have to take on. And needless to say, fusion, the nuclear fusion is one option. So we do believe that this will play a major role. That's how we are looking at it. So with this positioning, we would like to promote the policies related to the promotion of the fusion energy. Whether we are able to have the power generation in the year 2050, I'm sure many people would have different views on that. Last week, there had been an opportunity for me to discuss this issue with the representative of the Chinese government, and China is now looking at the realization of the nuclear fusion for their power generation. I asked him, when do you think that will be realized? And so that was a direct question. Do you think they can make it in 2050? And then, as a Chinese person, he was very cautious. He said that 2050 might be the extended goal, but maybe by the year 2060, that would be realized. So that was a kind of answer given by the representative by China. And then, what about EU? When I speak to, or when I look at the roadmap of EU, they would not say 2050, but in the 2050s. So that means that the nuclear fusion will be realized in the 2050s, not the 2050. So, but still, it is important to make sure that this will be realized as early as possible, so that every household will be provided with the energy given by the nuclear fusion. That's our final goal. So this is about the policy. Now I'd like to change the attention to ITER side. So I prepared some slides, but this has been already covered by the Director General of the ITER, and I'm sure this will be covered again by the following presentations. So I'd like to speak about what took place last month. And last month, the 7 participants joined the ITER Council meeting. So the most important is the impact of COVID-19. All the participants wanted to know how much the impact would be. So all in all, we have to say that the impact would not be assessed properly. So until it is time to be able to understand the entire picture of the impact, we will maintain the current goal of first plasma at 2025 that was agreed upon. And one more thing related to this, the Council, is about the test blanket module. We were able to agree on certain things. In the last several years, there have been some discussions about the participation of the countries. So all the participants wanted to join the TBM, test blanket module, and at the last month's the IC27, we were able to have agreement. So 4 participants are going to be joining the TBM, and Japan was one of the 4 participants. So this way, we are able to feel secured that we will be the full member of the activity of TBM. And I'm sure Rokasho Institute will report on the TBM, so I will not speak about it too much. This is about BA. This is a progress in BA activities. And then they are aiming for the realization of first plasma in 2025. And I also understand that this steady progress is being made in Rokasho. Many of the European engineers were not able to come into Japan properly because of the COVID-19. But BA activities are very important, and all the people are in agreement with this. And so with this, with the request to the government, we are now able to enable the European technicians and engineers to come into the Rokasho or other institute. So I'm very much feeling assured. So we are now getting into VA phase 2. The contract had been assigned. This is the SC. And then I'd like to speak about the budget. And this week, as a matter of fact, the budget compilation was made for the next year. And this has been determined. Next year, for ITER, well, actually, as can be seen here, this year we have the 165 billion yen, and next year we will have a budget of 178 billion. So that means, 17.8 billion. So this is a huge increase from 16.5 billion this year. And then about the BA activities, again, the figure this year was 4.9 billion, and next year, including the supplementary budget, the figure would be 5.9 billion yen. So again, the necessary amount of money has been already secured. So this is the kind of process that we have for the budget issue. And then for the LHD, for the large helical systems and others, we are steadily moving toward the realization of these goals. And I have prepared some the slides for the applications, but I'm sure this will be covered by the presentation by Rokasho Institute, so I'd like to speak them. So finally, I'd like to speak about the demo reactor. So today we discussed this issue of ITER DBA, but here I'm talking about the demo. This is the first step for the power generation. So demo activity is of the essence for that realization of the goal. So I'd like to share with you some the approaches of Japan. And here we try to promote the demo. And this is promoted by the nuclear fusion, the nuclear fusion strategy. So again, this is done by Committee on Future Science and Technology. Many people say that the Europe or EU is advanced, but the EU itself has not written down the roadmap, but the Eurofusion, which is a dedicated agency, has already written the roadmap. But in the case of Japan, the government itself is the owner of the roadmap. So that means that Japan or Japanese government is very much more focused and determined to promote this activity. Then also for the roadmap, we can say that there have been the successive roadmaps created in December 2017 and the July 2018. And then for we have the milestone for the 61 SA. So the next year, in 2021, we will work on the assessment step for the demo. So again, we will have the interim check and review, or C&R, in 2021. So we have the involvement of the Fusion Science and the Technology Committee of MEXT, which will work on the CNR. So that means that we will be able to look at the steady progress of the activities, and based on that assessment, we will decide whether to go on to the next step or not. So again, this assessment, the activities will take place next year. So I'm not able to report on that, but we are very much committed to to face squarely with this. Actually, the interim report or interim assessment is going to be done in Europe. So gate review is going to be done. Well, actually, they have already completed this process, and we were able to see the report last week. So EU is now looking at the assessment based on the interim report. So the demo is an international competition arena. So we'd like to make sure that we will not be beaten by the activities of EU and other countries and participants. Time is limited. With this, I'd like to close my remarks. Well, actually, this is a roadmap. So this is the last the slide. This is a roadmap. And this is CNR, check and review. It will take place at the next year till the end of the year. And then CNR will take place after the first plasma of ITER. And then in 1932, we will look at the success of ITER plasma. And then we will decide on whether to move on to this commercially. So that's how we are looking at it in the blueprint or the roadmap. That's all for my report on the Japanese situation of R&D for the fusion energy. Thank you very much.
Thank you, Mr. Iwabuchi. Next, we have Deputy Director of the Naka Fusion Institute of QST, Dr. Masaya Hanada. He'll be talking about the progress of ITER equipment manufacturing activities and integrated commissioning of JT60SA. Dr. Hanada, please. Thank you. I'm with the Naka Fusion Institute of QST. My name is Hanada. I'm pleased to be here. So I'm going to talk about the ITER equipment fabrication activities and integrated commissioning of JT60SA. So based on I'll be talking about the progress of these activities. Also, you have a live telecast from on-site. And I think this has been mentioned several times already. Prime Minister Suga, this October at the Diet session, declared that Japan is going to have net zero carbon by 2050. So he declared carbon neutrality, a decarbonized society by 2050. So in decarbonized society, we need power generation. And Dr. Tokimatsu has done research on this. Sorry. And so coal thermal demand is going to decline over the years. In 2050, nuclear fusion is going to appear, and that ratio is expected to increase. And in a decarbonized society, well, fusion is expected to play a major role. And this is how nuclear fusion works. So you have the deuterium and tritium, and you have high-speed neutrons. And then in the blanket, kinetic energy is converted into thermal energy, and so steam is generated that drives the turbine and generates electricity. So it doesn't use fossil fuel, and so has no carbon emissions, very green. And so this is how we move forward. So we are here right now. So we have the ITER and the BA. Those are the two wings of the bird. And we're moving toward power generation in the future. So at ITER, the burning plasma should be demonstrated. And also, nuclear fusion reactor engineering technology is developed. And also, JT60SA is supporting ITER and has advanced research looking at economics. So first about the ITER project. And this is an international project participated by Japan, Europe, US, Russia, India, China, and Korea. So sustained burning is expected, 500,000 kilowatt, and Q ratio 10 is expected. And the organization, well, Dr. Bigo leads the organization, and the former QST member, Dr. Tada, is the Deputy Director General. And this is the ITER site. My data is 1% older. It's now 71% completed. And so these are the equipment that Japan is procuring. They all require advanced technologies. And what's shown in red, I would like to explain in more detail. So first, production of the superconducting toroidal field coil fabrication, 33 conductors, 9 winding wires, 19 structures, and that will be integrated into 9 coil bodies. So this chart here shows the fabrication status as of now. And so structure and winding. Green is where it's already completed. As for the structures, about 80%. For winding, 70% already completed. And the integrated body, 3 have already been completed. And we have a thick-walled structure, and we have established a difficult welding technique for this large, thick-walled structure. It's 16 meters high, 9 meters wide, and 300 tons. And we have very high precision. And so we have completed this huge coil, unprecedented feat. And this is the ceremony of the completion of the first coil in January 2020. It's very huge. And the first one and the second one already has been carried to ITER. Unit number 3 expected to be shipped in January 2021. Next, the neutron beam injection heating system. So the particle is heated in the plasma. So 1 million volts, very high-speed beam is going to be injected into the plasma. And before making the actual equipment, we established a test site in Padma in Italy. And Japan has this advanced technology. So it was in charge of the direct current, ultra-high voltage power supply. And the power unit already has been built. And in Italy, it has already been installed. And although there is COVID, we are connecting Italy and the QST. And so test commands are being sent from QST, and output tests are now being conducted. Next is high-frequency heating equipment. And so electromagnetic waves used for frequency. 28 of the 24 by Japan. 7 already have been manufactured. And the gyrotron that have been made, well, within QST we have done testing. And we have already conducted testing on 3 units, confirmed that it meets the required performance. Very demanding performance requirements, but we were able to achieve that. We already have 3 units that have met those requirements. And diverter. So this is placed here to protect the vacuum vessel, shaped like this. And if you break this apart, it looks like this. It's tungsten monoblocks, and on this surface there will be heat, and by having water you will cool that. So these blocks will be placed on top of the structure, and so we're starting the manufacture of the materials with target completion of 2023. So 200,000 tungsten monoblocks for the actual equipment and 120 sets of stainless steel forging to support structure and 1,500 cooling pipes of chrome, zirconium, copper being completed. And a plasma measurement device, Japan is in charge of 5. And so we do a test, prototype, and we show 2 examples, microfission chamber. And so we have developed a high precision copper plating technology for polarimeter. We have developed a new reflective mirror for that. And through these elemental technologies, we're conducting prototype development, and final design is being conducted, and we're moving forward with the procurement. And blanket, remote control. And for this vacuum vessel, it's high radiation, so people cannot come in. So we made a monorail like so, and the robot is placed here. And using the robot, we do the maintenance. So blanket module is going to be maintained by Japan. And so this robot arm has been made, and tool to fasten the bolt have also been made. And so we improved the torque system to parallel link, and we have made it much smaller and lighter. And with this, remote handling is going to be conducted at ITER. So different topic, going from ITER to JT60SA. So JT60SA, 3 objectives. One is to provide support to ITER. The second is to supplement ITER toward the demo reactor. And the third is develop human resources to lead ITER and demo development. In terms of supplementing ITER, to have a long-term high-pressure plasma. And by realizing that, we can make the equipment smaller, make it more economical, and can have economical steady-state equipment. So this kind of high-pressure plasma is being expected. And at JT60SA, we're going to develop a long-term high-pressure plasma similar to demo. So this is the division of labor between Japan and Europe. So these are all the equipment. And it's about 50-meter high, width about 12 to 13 meters, and about half the size of ITER, but the superconducting coil size is 10 meters. So until ITER is completed, this is the largest tokamak test facility in the world. And this equipment, well, the assembly will start in March 2013, or rather started in March 2013, finished in March 2020. And so cryostat base was made in Spain. And 2 years later, the vacuum vessel was installed. Then 3 years were spent in Europe to make a toroidal magnetic coil, assemble that or install that. And the body of the cryostat last year, and the central solenoid installed last year. And the cryostat top was installed. And this year, March, assembly was completed. And this is the cryostat lid, 11.6 meter diameter, very big. Use a special jig to lift it and then place it on the top of the machine and complete it. So inside the vacuum chamber, you see here, in order to protect it, you have this kind of carbon tiles, so that is placed there for heat protection. And JT60SA assembly, well, we had 10-meter equipment that needed to be assembled at 1/10,000th precision, and that's going to be useful for ITER. And this is how it looks now, JT60SA. So assembly was completed March this year, and now integration, coordination, test operation is being done. And was mentioned earlier that the JT60SA has shifted to phase 2 from April 2020, and the project was extended. And right now, we have this kind of plan for the future. So it's December 2020. We're doing integrated testing. From January, we're going to start using plasma for test operation. And then we're going to enhance the equipment, do testing, maintenance, then some more experiments. And so from April this year, as part of the integrated commissioning, we finalized the location of the piping and the wiring and conducted testing. And from September, we started vacuuming, and the superconducting coil was cooled, and the cooling vessel was baked. And so this is the central control room during the commissioning, and cooling the superconducting coil. You see the resistance vertical axis, and on 26th of November, resistance went to nearly zero. So all of the coils transitioned to superconductivity. That was confirmed on 26th of November. From this week, we are actually applying current to the coils and conducting such testing. And so we have experience at JT60SA, and we're going to deploy that to ITER to lower the R&D risk. So November 13th, 2020, we signed a memorandum, and in 3 areas we are collaborating. Assembly of tokamak and integrated operation plasma experiment. And we held a workshop in October and December and reported our experience. And in the integrated commissioning, the ITER researchers are joining the weekly integrated commissioning conference of JT60SA. And from second half of November for 3 weeks, the ITER organization expert joined the JT60SA work, and that was featured in the ITER newsletter. This is Mr. Maeka from IO, and this is QST person, and FOE person, another partner, so 3 people in this photo.
Here at this point, we'd like you to listen to the report from the actual site. Actual site being the Naka Fusion Institute. I'd like to tell you what kind of things will be covered in the presentations from the site. The ECH launcher, vacuum exhaust equipment, and the also positive ion NBI cold terminal box, power feeder, valve box, and the negative ion NBI. This is the JT60SA main unit. So the director, Mr. Moriyama, and the deputy director, Mr. Ide, will speak about this. Mr. Moriyama, Mr. Ide, are you ready? Thank you very much for your introduction. This is the JT60SA Central Control Room at the Naka Fusion Institute. The semiconducting coils are currently being tested. As you can see, we are conducting we are conducting the performance test to work on the coordination. Please take a look at the panel. As you can see, the temperature of the coal is 4.6 K in absolute terms, and the superconducting state is being maintained stably. So today, as a report from the Institute, I, Moriyama, will first introduce the main body of JT60SA, which was completed in March, and then Ide will explain about the ongoing excitation test, the performance test. Thank you very much for your cooperation. First, let's take a look at the inside of the room. There are about 50 members of the operation team, including the test operation supervisors. There are many surveillance cameras in the JT60SA room, and we can check the status of the SA and its attached equipment from the central control room. Today, we will first make full use of these cameras to introduce each of the SA that was completed in March. The main body of JT60SA is 16 meters high and 13 meters in diameter, about half the size of ITER. And what you are seeing right now is the cryostat, which is an adiabatic vacuum vessel, and inside is a 10-meter diameter donut-shaped vacuum vessel that confines the plasma. And the superconducting coils around the vacuum vessels are cooled by liquid helium. You see 28 of them. A valve box containing valves for liquid helium distribution is located on the top of the cryostat and is a main feature of the SA's appearance. There are 11 of them in total, and you can see 5 of them. I switch the camera to the helium supply line. The cryo line supplies liquid helium to the superconducting coils. This is a cryostat. It is connected to the cryo system on the other side of the wall. The liquid helium or the gas helium with a slightly higher temperature is here. So you have this thick pipe, and inside of this is vacuum. And this way you are able to keep the temperature. Let's look at the situation beyond that. You see the feeder lines. The current feeders, on the other hand, supply the coils with a current of 20 ampere per line. It is connected to the power supply system in another building via feeder line on the other side of the wall. The length is about 150, and the current feeders are able to supply the coils with the 20,000 ampere per line. So here, it is the interface between the atmospheric pressure and room temperature world and the vacuum and cryogenic world through the high-temperature superconducting leads procured by Europe. Next, you will see the heating systems. The large blue structure is the negative ion neutral beam injector, or NNBI. The ions are accelerated at a high voltage of 500,000 volts, and particles with a temperature equivalent to 5 billion degrees Celsius are injected into the plasma at several tens of millions of degrees Celsius and heated to a temperature of over 100 million degrees Celsius. If the ions are injected as ions, as is, the orbit of the beam will be bent by the plasma confinement magnetic field, so the beam is injected as a neutral atom beam through the gas. Switching the cameras, this is the launcher of the electron cyclone heating ECH system. The electromagnetic waves are injected into the plasma to heat it like a microwave oven. And Mr. Hanada talked about the gyrotron. So again, the waveguide, a metal pipe connected to the upper right, transmits and injects 1 megawatt of power per waveguide. And there are 4 turbo pumps connected to the manifold that you can see now. So you see the connection within the cryo system. And then to the left of the vacuum exhaust system are the ports for instruments. Temperature measuring devices are attached to the end of a long tube called the port plug. It looks at temperature and the density and also the state of plasma. Then let's turn the camera back to the front. As was mentioned by Mr. Hanada, the most important thing to keep in mind during the assembly of this huge JT60SA device was to improve the installation accuracy. The accuracy of the confinement magnet field had to be 1/10,000th of a meter, so we had to mount and install a 10-meter class device with an accuracy of 1 millimeter. So from now, I would like to share with you the kind of equipment that I have just talked about. So next, I'd like to introduce the teams or groups that operate the numerous devices I have just talked about. The main unit group monitors the operation of the vacuum pumping system, gas circulation system, and gas injection system. And then the coil refrigerator team operates and monitors the cryo system that cools the superconducting coils and also measures and monitors the superconducting coils. And the power supply group operates and collects data from the power supply that supplies current to the superconducting coils. Lastly, the RF group, the radio frequency group, operates the electron cyclotron heating system and collects data. They work together to work on the commissioning. So let's take a closer. Let's ask Mr. Ide to speak about the commissioning. As was mentioned, we are now in the process of conducting the performance test. This is a test to check the operation and the soundness of the equipment, including the power supply, by passing the current to each superconducting coil little by little. In conducting performance tests, we have to first and foremost come up with the patterns. The first step in the test is to create pattern for the current to flow. Let me explain to you, or actually show you, how we are doing it. This is to set up the conditions. First, as you can see, we specify the current value for the first point and also write the value for the last point. And then you have new points here. For example, if you add a point like this, you will have a waveform of the command condition for the current test, and then this should be saved with the sequence. And this way, you are able to have the performance test based on the instructions. So here, we share with you the kind of data that have been already conducted beforehand. This is the wave, the form. So you see that this is already instructed from 0 to 100. So the command condition is shown as a straight line. What I just created are the command values from 0 to 110 seconds. And the power supply side has predetermined as to which timing to start up toward the command location and how to lower it. And so we did not use actual coil, but rather the quasi-coil had been used. So I'd like to share with you the demo for that. So as you can see, this is a starting point, and then you can see that the current is flowing as instructed. We are running out of time, so the video is in fast motion, but let's get started. And then, as you can see, the power supply is generating current according to the conditions we have created. So this is the purpose of this test, is to see if it is done according to the instructions. We will first perform these tests separately for each of the 11 power supplies for out of the all 28 coils. So for that means that we work on the testing of the power supply, 11 power supplies for the all 28 coils. the 18 toroidal coils will be used on a single power supply. And then after the individual tests are completed, a combined test of all coils and all power supplies are conducted to complete the current carrying test. And then after this performance test is completed, it is time for the plasma test. We actually generate the plasma and conduct the comprehensive test of the entire system, including the controllability of the plasma. Let's demonstrate how plasma is actually generated. To begin with, let me briefly explain what we are preparing for the plasma discharge. So this is the figure we establish. So you see the waveform like this, and then this is the shape of the plasma, and you see the parameters. We will decide the parameters for the plasma, and then here you can say that this is the discharge conditions, and then so the collection of the various parameters specified in this way is called the discharge conditions. And then now let's start the sequence. So I'd like to share with you the demonstration of the sequence that is based on the discharge conditions. When the sequence starts running, the coil power supply and heating system will start preparing to operate according to the discharge characteristics. So you are able to see this clearly. And then, as was mentioned earlier, you have the coil temperatures and the outlet temperature, cryostat pressure temperature, and the vessel pressure temperature. And then this is demo, but this is not in line with the actual situation in some cases. But you are able to see this, visualize this. And then this is the speed. And then you are able to see what is taking place here. And then again, there are several injectors, so you're able to see clearly what is taking place. And also, it is important to make sure that all the doors are closed for the safety concerns. So again, the screen is able to show how the safety is secured. And then this is a schematic diagram of the cross section of JT60SA, which has just changed 1 minute before the discharge. And the gray is a vacuum vessel. The D-shaped toroidal coil that confines the plasma is shown in blue. And in green is a cross-section of the ploidal coil, which controls the plasma current and the shape of the plasma. So the 30 seconds before discharge, the coil used to generate and control the plasma current turned red. So I think I have shown you the same thing at the performance test example. And so this way, you are able to have the 6 coils to control the shape of the plasma. So in order to confine the plasma, it is important to have the field set up. This is inside the vacuum container. So with the magnetic sensor, you are able to see the shape of the plasma. So this is of the JT60SA. This is the previous one, JT60. And then this was done by the actual plasma. So shown here is the left-hand side is image of the actual right-hand side is the actual plasma, and the left-hand side is previous device, and the center of the plasma does not produce any visible light due to its high temperature and appears rather transparent. This shining white area is the diverter region, which is used to receive heat and particles from the plasma. Now we have increased the heating power, and then it is calmed, and then the shape is getting smaller. I'm sure you heard some various sounds, including the whooshing sound, but these are the sounds of instability occurring in the plasma, and they can be heard because of the frequency is in the range where the human ear can hear them. So discharge has now ended, and then after this, we check the measured data such as the temperature and density of the plasma, as well as the information obtained from the images and sounds, and consider which part of the discharge conditions should be modified for the next discharge, and make the modifications accordingly before starting the next discharge sequence. And this is how the JT60SA experiment progresses. this is a plasma now. After such much adjustment, so in the integrated commissioning, we will start by turning on the first plasma and then gradually grow this plasma. Thank you very much for joining us for this short webcast. We conclude the live broadcast from the JT60SA Central Control Room and from the Naka Fusion Institute. I'd like to hand over the microphone to Dr. Hanada. Thank you very much. So this is a summary. The Phase 2 of the BA activities was jointly declared on March 2nd, and the JT60SA project started its Phase 2 activities in April 2020. The project within Phase 1 is progressing as planned, and assembly of JT60SA will be completed in March 2020. Then in April, as part of the integrated commissioning, the layout of the surrounding piping and wiring was finalized and tested. And then the vacuum pumping, including leakage tests, progressed smoothly, and the coil cooling started in October. And the milestone of the project was achieved. After performance tests of the coils, the plasma, the experiment will be ready in early 2021. I just read it. So for the early realization of the nuclear fusion, we'd like to continue working on it with full strength. So we'd like to continue asking for your full-fledged support. Thank you very much for your attention.
Thank you, Dr. Hanada, Moriyama, and Ide. Next, a special lecture from the Institute of Energy Economics, Japan. We have Senior Managing Director and Chief Researcher, Dr. Ken Koyama. He's going to talk about the COVID-19 pandemic and the international energy situation. Dr. Koyama, please. Good afternoon, and thank you for the introduction. Is the mic on? It is on. I'm with the Institute of Energy Economics Japan, IEEJ. My name is Koyama. I thank you for inviting me, and I'd like to spend some time to talk about, well, not the nuclear fusion, which is your main interest, but rather like to take a broader perspective and talk about what is happening in the energy world at a global scale. So 2020, this year, it was a dramatic year for energy. COVID, for one, that became a pandemic, impacted our lives. And the energy situation has dramatically changed. And I'll talk about that in more detail after this. It was not just COVID, though. And later I will go into more detail. But in the U.S., Mr. Biden has won the election. And under the new administration, new president, what kind of environmental policy is going to be pursued? That is going to have a huge impact on the world energy situation. And also, as many have touched upon, there is this move toward carbon neutrality all around the world, one country after another. I should not use the word boom, but major countries around the world coming up with target years for carbon neutrality. So in the world of energy, this can lead to revolutionary change. So there's COVID, there's the new administration in the US, and this wave of carbon neutrality. These all have a great impact, and we saw all of that happen this year. And so what do we need to think about going forward? Well, in terms of solutions, innovative energy technology is going to become necessary. That's what these developments point to. And your central theme, nuclear fusion, is going to be quite significant in this area. Sorry, it's very complex, but in a nutshell, the energy issue, the global energy issue, is impacted by international politics and energy geopolitics. So, who are the players in the geopolitics in energy? There are many, but it's U.S., China, Russia, Middle East. In regards to energy, these are the key players. Of course, Europe and Japan, India, they are also important players. But in terms of energy geopolitics, the interactions and the relationships amongst these major players is what we need to focus on. And what becomes important is what's at the top. So what's going to be the impact of the pandemic? That's one major factor. And also the outcome of the U.S. presidential elections. And also this move toward decarbonization. And also the most important conflict in geopolitics, U.S.-China conflict. So we have to think about all those impacts. So I said that there are four major players, and amongst them, the most important player that has the biggest impact on the world is the U.S. And the occupant of the White House is going to change. And what's going to happen under the Biden administration? Well, going back further, there was the Obama, then Trump, and then Biden administration. And especially in energy and environment, there has been major shift in policy. So we see the potential for a big pendulum swing. So overall, not necessarily all the policies will change, but in energy and environment, especially for climate change, President Obama made a great effort for the Paris Agreement. Then Trump withdrew from the Paris Agreement, and Mr. Biden is saying that he's going to return on the first day, and he's going to aim for carbon neutrality in 2050. And concerning energy, well, the Middle East is a big issue, and the nuclear deal for Iran was put together by Mr. Obama. Mr. Trump withdrew from that, Mr. Biden might return. And the shale revolution has been a big impact. How to deal with the shale is another big point. As an energy watcher, one thing I want to convey to you is that when we have the Biden administration in the energy and environmental area, I think we're going to see a clear message of major change. But that message, is that really going to result in actual change? We really have to carefully examine that, because there are limits to what the president can do, what the federal government can do. There might be such limitations. For example, people in the world, they're focusing on the runoffs in the state of Georgia to be held on the 5th of January. If the Republicans take even one seat there, it would be a divided government. So even if President Biden wants to do something, Congress may not go along. And it was the same with President Obama and President Trump. So they really used a lot of executive orders. And certainly there are limits to what the executive orders can do. And what's very important for the U.S. is COVID and economic reconstruction. And people saying climate change is important. But compared with COVID and the economy, well, as a prescription for that, climate change countermeasures is being looked at. So the message may shift dramatically, but what actually changes on the ground, we need to carefully watch, is what I want to say. So COVID, a very big issue for the U.S. And is it really going to be contained? That is going to be the key. myself and many people around the world, everyone around the world, all wishing for an early end to the pandemic in Japan, in Europe. But we see in Japan and Europe very serious second, third waves, very high expectations for vaccines recently. And in the market, there is somewhat optimism, expectations for a brighter future, but we really don't know what will happen because of COVID. In 2020, we had the worst economic situation since the Great Depression in the 1920s and 30s, minus 4.4% global economic growth. You recall how difficult it was under the Lehman shock. At that time, it was only minus 0.7% negative growth. This year, it's more than minus 4, much larger. And the global energy situation is going to be quite impacted by that. And also, it's not just about economic growth. There has been lockdowns restricting movement of people and goods, and it's necessary to prevent infections. And if that happens, of course, there will be much less demand for energy. That's what happened in the first half of this year. So we say that the energy demand evaporated. So demand evaporation was a phenomena that was observed in March and April, as I see it, and energy price plummeted. And that caused a market reaction. Now, long term, how is COVID going to change the world? That is another issue that this situation is raising for us. So this simple graph says that next year, oil demand, global oil demand, is all up to COVID. So red line, the dotted line, is under the assumption where we'll have severe COVID situation continue with the second, third waves. If that should prevail, the recovery of demand will be very weak. If we can contain COVID, we can have the solid line. So maybe not back to 2019 levels, but a good recovery can be expected. So if energy demand continues to hit bottom, what will happen is something we really have to think about. So in the energy market, there was a shocking event. What is this graph? This shows crude oil prices, future prices. And the 20th of April this year, this future price went to minus $37. What does it mean that it's a negative figure? Seller is desperate to find a buyer. They couldn't find any buyers. And the futures market is trading for the future. And the next day, it's no longer the future, it's the present. And you have to actually exchange oil. So you're desperate to find people who will take the oil, and I will pay you to take the oil. So that's an abnormal situation. Seems that there was this huge oversupply, which was caused by the demand evaporation, which led to these negative prices. But after that, prices have recovered. Why? Because on the supply side, they made effort to reduce production.
I'm sure you have heard the term OPEC plus. OPEC meaning Saudi Arabia and other countries, oil-producing countries, and plus meaning the OPEC plus Russia. So the oil-producing country that is not a part of OPEC will work on the reduction of their production. So these oil-producing countries are very much committed to the reduction of the oil. So about 10% reduction has been made based on the strong commitment by each country. And then regardless, this is irrelevant to the production, irrelevant to the government the policies. There has been a sharp decline of the production of oil in the United States. This is based on the market demand. So they are very much expelled from the market because of that. So that means that they are driven out of the market based on the market power, but the other parties are reducing the oil production based on the government policy. What will take place next year? So based on what we see, you see the trend of the demand in blue. If you see the control of COVID-19, you will see the increase of the supply. So with this, we are able to see the stabilization of oil prices. But there are some uncertainties, I'm quite sure, whether there is a production of shale oil in the United States, and also whether we are able to actually control COVID-19 or pandemic thereof. And also, when I created this chart, this was not a problem. For example, what would be the situation between the United States and the Iran? When the Iran come back to the international arena, then what would be the implication of their production of oil? These things have not been taken into account when I created this chart. Nobody knows what would happen. Then next, the theme is the LNG. This is the second largest energy source, only second to the oil. And this will also be impacted by COVID-19. And this is LNG, and this is natural gas. And also on the right-hand side is LNG. I'm quite sure you all know that liquefied natural gas. This is a very important energy source for the power generation, especially after the great earthquake. There was the close down of the nuclear power plants, and then the central pillar of the sources of the energy was LNG. But because of COVID-19, they are in the state of the excessive demand, excessive supply. So this is the next chart. So we have been looking at the situation of the excess demand, excess supply, and the blue shows the supply, and this is even without the COVID-19, it was considered to be the excess supply. But even after the COVID-19, situation would not change. So that means that supply would be abundant, and where the demand is much smaller. So that means that, as in the case of the crude oil, the price would go down. And this is a busy slide. You might have difficulty understanding what it is. There are only two lines that I want you to look at. One is the orange, which is the LNG spot price. It shows the balance between the demand and supply. And then this is you see the decline for the 1 million BTU. So in the case of the LNG, million BTU is a unit, and it is going down to $2. And then after that, the LNG started buying a huge amount of LNG, and also there have been some the troubles for the supply project, and there has been a little bit of recovery of the price. But still, because of the demand and supply, there has been a sharp decline of the price. And another line that you want to look at is the violet. This is the Japan LNG average. So this is the kind of the price that Japan is purchasing. Why is it that it is fluctuating? Well, this is very much linked to the other issues, or to the petroleum or oil. So the LNG is very important for the power generation. So in what way are we able to purchase their power sources? So that's the ore materials. So that's something we have to focus on in the years to come. But there has been a huge gap, maybe because of the COVID-19. So COVID-19 is not the direct source of the problem, but rather this has made it clear for us to see. So whatever the case, you see the decline of the prices of the oil and also LNG. So that means that energy industry will see the decline of the demand and the increase of the supply. In order to survive, they have to work on the cost reduction, and also they try to organize themselves for the reduction of the expenses. So that means that they have to reduce the amount of investment. The oil majors and the large companies in the oil-producing countries are now reducing their investment by 20 to 30%. And if this situation continues the next year, then they will continue reducing their investment. So if the COVID-19 will be controlled, and then if you see the rebound of the demand 3 years, 4 years, 5 years from now, then that means that we will have to face with the problem of the rising prices, because they are not making investment here. They do not have capacity. And also, they are very much dependent on the oil-producing countries are dependent on the income from the oils. So because of the decline of the prices, they are now having a difficult situation. And also within the countries of the oil-producing region, they are suffering from pandemic. So that means that economically and also socially, they are at a loss. So we are not quite sure whether they will continue their stable situation in the years to come. So at this moment, we have the decline of the price of the oils, but this would lead to the instability in the future. That's how we have to look at it. And then I'd like to speak about long-term view of COVID-19. With COVID-19 and the pandemic, how the world would change. So we have a dedicated team for the creation of the scenario. So we have the post-COVID, the world-changing scenario. Simply put, we are suffering from COVID-19 this year, and we have the change of in the political and economic and social the standing, and this shall be maintained even after this year. And there are two words. One is digitization, and the other is the importance of the security. Before COVID-19, the most important was to reduce cost. So that was the only thing that we had to be worried about. For example, in the case of free trade, it is important to reduce cost. But after COVID-19, we no longer are able to worry about the prices, but rather we have to make sure that what is necessary should be maintained, or if it is necessary should be secured within the country or maybe among the allied nations. So it is important to pay more attention to the supply chains. In what way are we able to continue having the supply chain? This will change. And so the new system between the structure between the China and the new Cold War, between the United States and China is the representation for that. So the society would be driven by the digital technology, information or IT technology, so people would not gather anymore. So the IT technology will drive the people's activities, so things will change. And this will have a major implication for energy. For example, the energy, the security would be something we have to focus on. Energy sustainability, the self-sustenance is important. Strategic energy development, energy technology should be developed within the country. In this scenario, what will happen?
Cost minimization, and it's not going to be cost minimization and economic efficiency. There's going to be focus on security. That will lead to lower economic growth. So 10% down from blue to the orange line. So in the post-COVID scenario, global GDP is going to decline by 10%. And it's not going to be even where it's going to decline. Earlier I talked about the supply chain. If supply chain may move away from some countries and move to other countries. So supply chain will flow out of China and move to India and ASEAN. That is our outlook. As a result, energy demand as a whole will decline, and there will be shift from China to India and ASEAN in terms of energy demand. Well, energy demand is going to be centered around Asia. That's our view, as well as others. Under the post-COVID scenario, there's going to be shift within Asia. Another important point is about oil. With the change in the societal structure, oil is going to be hit because people will not move, and there will be peaking of demand. So on the right side of the slide, you see there will be a shift from blue to the orange line. And at 2050, 14 million barrels per day demand decline. And our analysis shows that the oil will hit peak demand. Well, you might think, COVID may not be that big an impact in terms of demand decline. Maybe because you've seen a graph like this. So it shows various organizations' long-term outlook. So orange shows that the long-term demand is going to fall immediately. And there are many such outlook. Compared to that, the graph I showed you may seem quite moderate. But there's actually a secret behind this. The orange line here This is after strengthening global warming measures. And in order to limit temperature growth to 2 degrees C, this is how much you have to constrain oil demand. It's backcasting. So the COVID projection is different from that. That is just impact to demand from COVID. And if you add on to that the demand decrease due to environmental measures, it's going to be much larger. So just with COVID, I showed you that there's going to be peak demand. Now, if oil demand should decline drastically, that will impact the oil-producing countries' economy and the oil-producing system on a global level. And what will replace oil will be electricity, because there's going to be a lot of digitalization. Even without COVID, there was going to be a move toward electrification. But electricity importance is going to become even larger with COVID. And what would that entail? That's something we have to think about. So power, electricity is going to be more important. And I think there are 4 keywords related to this. One is decarbonization. Second, deregulation. So market deregulation. Third, digitalization, which we've been talking about. And then number 4, decentralization. So these are the 4 Ds. And these keywords are going to drive the power sector. And the issue is that these 4 Ds impact each other. They're interrelated. And sometimes there's a trade-off between them or amongst them. The top 2, decarbonization and deregulation. Well, deregulation, you liberate and you introduce more competition. If you introduce more competition, the people will choose the cheapest solution. Maybe it would be coal. Realistically, that has been what has been happening, and that could happen in the future. So promotion of competition through deregulation and decarbonization, they are not necessarily a good match. And this is something that we have to think about going forward. And if electricity is going to be more important, well, it has to be affordable. And stable supply of electricity is going to be increasingly important. And there is this additional challenge of intermittent renewable energy increasing. And there are new threats like cybersecurity. And so concerning power, innovative technologies and approaches, including the issue of nuclear fusion, going to be quite important in the power industry. Now, talk about carbon neutrality and the decarbonization. And so there was a wave this year, as I said earlier. So the EU has been talking about carbon neutrality in 2050. They have been talking about that previously. And they put together a Green Deal even before COVID. And that focuses on renewable energy, hydrogen, clean mobility, and energy conservation, energy efficiency. So they're going to promote those clean energy measures. And Europe is going to grow over the long term based on that. So that was a long-term growth strategy. But with COVID, European economy has been impacted or devastated. And now they're going to use this to revive the economy. And China, in September, Xi Jinping said that China will target 2060 at the UN General Assembly. Next month after that, Prime Minister Suga said 2050 will be the target year for carbon neutrality. And soon after that, Korea made a similar pledge. And if Mr. Biden becomes president, U.S. will follow. So Japan, U.S., EU, China, Korea, these 5 countries and regions, they account for about 60% of CO2 emissions. from energy. So they have some difference in terms of the timing, 2050, 2060. But if they really work toward carbon neutrality, it's really going to shift the momentum at the global level. But carbon neutrality, this is really a challenging target. That's something we shan't forget. And I'm convinced that this is not going to be easy. Our current energy system is dependent on fossil fuels, 80 to 90%. To make it carbon neutral, you really need revolutionary change to achieve those targets. Even for a developed economy, it's difficult. And for emerging economies, developing economies, is it really going to be possible? It's going to be very difficult. I mean, there are some prescriptions, as I list on the third bullet. Well, first you need to conserve energy. Don't use energy, and use non-fossil fuel, like nuclear or renewable, as much as possible. And also you should promote electrification, because the power sector, compared with other sectors, relatively is more easy to make zero emission, because they already exist zero emission power sources, nuclear and renewable. So electrify and make the electricity zero emission. But you can't make 100% zero emission. And I think highest you can achieve probably is about 50%. So the remainder, how to make that zero emission, that's going to be an issue. Perhaps we will need some new energy like hydrogen. So this year, at the G20, well, Saudi Arabia hosted or had the presidency of the G20, and they proposed the circular carbon economy, and Japan is agreeing to this. So GHG that's emitted into the atmosphere, take a comprehensive approach to reduce, reuse, recycle, and remove these carbon. So comprehensively, carbon should be removed is the idea behind this concept. So reduce would include nuclear and renewable and other technologies. But using these technologies, focus on decarbonization of the world, that should be possible. And currently, fossil fuel is providing 80-90%. Use that also to promote decarbonization. That was the idea. And so I won't go into detail of this.
This is a busy slide, but for us, we are able to understand to what extent the new technologies can be incorporated. And this is based on the calculation that I have just outlined. And then this shows the CO2 emission in the world, a reference, the progress of technology, CCE 20. When I say reference, the business as usual. So that means that the entire world will not change. So that means that we will see the increase of the CO2 emission as is. So this is reference. Then progress of the technologies. We have advanced technologies, and if we are able to utilize the best out of everything we have at this moment, and then we are able to go that level. And then CCE is something I talked about before. So this is the carbon, the CCE, the circular carbon economy. And this way, we are able to reduce the 56 tons of CO2, as can be seen here. And the most important point here is shown on the right-hand chart. This is a bar chart that shows the primary energy demand. Here you have the actual CCE and also the technology progress. So that means that you see you are able to reduce the carbon emission drastically without drastically reducing the use of the fossil fuels. To what extent are we able to explain this? Well, you see the clean the hydrogen. If you are able to have the penetration of the clean hydrogen, then you are able to reduce the CO2 drastically. And so this is based on our analysis. Of course, these advanced technologies could be implemented. So the prerequisite for that is to have the infrastructure that would enable the reduction of cost. That is the hard work. But for the carbon neutrality, it is important to utilize all the technology. We have to utilize all the options, all the alternatives, and then only after that you are able to achieve this situation. And one more thing that is important is also about hydrogen. Hydrogen can be driven or generated by many things. I'm quite sure. Needless to say, that you are able to come up with the carbon-free the hydrogen from the nuclear power generation. Also from renewables, you are able to produce the hydrogens. And also, as can be seen here, it is possible to come up with the hydrogen from the fossil fuel. So that means that you are able to utilize CCS. So this is also very innovative. And with the combination of all these, you are able to generate hydrogen. So blue is from RE, the yellow is from the nuclear, and also the green, the blue from the others. So that this way you are able to come up with the new hydrogen society. In order to reduce carbon drastically, you try to see the sharp rise of the demand of hydrogen in the entire world, especially for an LNG. For the fossil fuel, it is utilized, and then again, you see the important export of hydrogen. So if you have the green hydrogen or yellow hydrogen, again, then a different pattern of the transport, the sourcing of the hydrogen would occur. So if you are talking about 2050 or beyond, then depending on the innovation, depending on the technology realization, things will change in the entire world. So allow me to speak about the impact of energy transition. This is quite simple, but what we are seeing right now is the situation where we do not have a chart. So even if you are in navigating on a vessel in the sea, so we are faced with the energy transition. We do not know what to do. Actually, what would make sense? So we are now depending on the fossil fuel 80%, 90%, and then we are now getting into the world where the fossil fuel would not be the one we are able to depend on, and the carbon neutrality is something we have to aim for. However, up until now, the world had not been able to experience. Well, actually, the world had been able to work on the energy transition. Even before the Industrial Revolution, the entire the globe had been dependent on the natural energy, the animal, the labor, and also the wind power and hydropower. So this had been the case before the Industrial Revolution. And then after the revolution, we had to develop the industry. So we needed to have the energy. And there they used the coal back then. And then it lasted for many years or many decades. And then in the 20th centuries, we saw the increase, the century of the oil. And the background to this was the very sharp rise in the level of the technology. We saw the deployment of the automobiles, and it lasted for many decades. And now we are seeing the changes. So what should be the triggers for the changes in the past? I think the successive oil crisis in 1970s was the starting point of the change. So we had been focusing too much and also depending too much on the Middle East, and Japan and although other countries had a difficult situation with the oil crisis. In order to overcome that, they tried to come up with the technologies that would be the alternative to the petroleum. Especially noteworthy was the deployment in the advanced nations. So this way, we were able to see the reduction of the demand for petroleum. Japan was one example, but still, developing countries are still utilizing the fossil fuel, the oil. So we have to say that oil is a leading energy source. So we have to say that this need or demand will remain as is for quite some time. But again, 21st century is a time where we have to make decisions. So carbon neutrality is the aim we have to have, and we have to secure the security of the energy. And as can be seen, the post-COVID-19 structural changes may influence energy transition. This influence might be huge. And also one more thing that we have to consider is the intensifying technological hegemony. So I talked about the energy security issue. Who will be able to control the new technology? Who will be able to come up with the new technologies which will be dominant? So that will be the hegemony we can think of. I'm sure you see the very high tension between China and the United States. This has been widely covered in the media. So you are seeing the strong clash between the two countries. So this is very much related to technological supremacy. So I think it is fair to say that this is about the technological supremacy. Many people say that this is only about IT, but this is also applicable to energy. Who will be able to lead this kind of energy transition properly? Who will be able to get a hold of the technologies which would enable energy transition? And this way, we will see the change of the world order. I'm no expert here, but I can safely say that this will be applied to the nuclear fusion. So against this backdrop, Japan is no exception. Japan has to come up with an energy policy which is in line with the changes of the situation. And the previous speakers talked about this, but we are now going back to the energy mix. So we have the energy we are in the process of basic energy plan. And then the fifth basic energy plan had been agreed upon at the cabinet meeting in 2017. And they have the energy mix goal for 2030. But and I was a member of the advisory committee, and we had to have a very difficult discussion, and we tried to come up with the numerical target. So 20 to 22% of the renewable for the entire power generation. So we were able to have the numerical target, but we have to say that there could be the problem of the restart of the nuclear power, and also the cost issue also is very important, the problem associated with the renewables. So for the 2030 goals, there are many problems. But now we are faced with an even more difficult issue, which is the long-term issues that we have to incorporate into the next basic energy plan, which will be the sixth basic energy plan. We would like to establish the basic energy plan next year, and the full-fledged discussion has already started. And then this should take into account the kind of new strategy, new situations surrounding Japan. It should deal with the new environment, including the impact of COVID-19, and also the way Japan would engage with the United States, with the President Biden as a head of the state. And so the Japan-U.S. relationship is the single most important relationship between Japan and other country. So under the Suga administration, Japan would have to adopt new concept, a new way of thinking. And then in the new concept, that should be the most important would be the carbon neutrality goal till the year 2050. At Abe administration, the GHG reduction of 80% had been the goal by the year 2050. 80% is a huge goal. I was convinced that it was very difficult. But now we are thinking about the 100%. So this is carbon neutrality. And then what should be the energy mix to realize that? So we will spend the next 1 year within the advisory council to speak about that. But most important in Japan is that when establishing the next basic energy plan, we not only think about carbon neutrality, but also we will think about 3 E's, and also we have to think about S, which is safety, since we experienced Fukushima accident, and also for the 3E, energy, the security, and also economic efficiency are also important things. So in the next basic energy plan, we have to come up with these things. For carbon neutrality, target has been already presented. And so we have to work on the energy security and also economic efficiency. All three should be filled alongside with each other in the new basic energy plan. And then against that, we have to consider how we deal with nuclear power, the renewables, and also other issues related to specific the fossil fuels and also hydrogen energy. So we have to have individual the specific measures and policies for each and every one of them. In order to establish that, the government should come up with a policy, but that's not enough. We have to deal with the major transition, energy transition. So the most important is the engagement of the private sector and the private entities. So these people would have to participate in this because they are the ones who are able to come up with technologies. The major strategy and also the policy should be established by the government. But enablers are the players in the private sector. So they will have to advance their technologies and finally work on the commercialization, especially for the 2050. We have a long-term view, so it is indispensable to think about what you have to do, which is aiming for the commercialization. So this is the last slide. Simply put, what we have to do is that we just experienced the unprecedented year in 2020, and we will continue to see unprecedented years down the road. And then after this kind of upheaval, we have to say that the future is not clear. And against that backdrop, we have to come up with the strategic approaches. Without that, Japan will not be able to survive socially or economically. In order for Japan to continue having the presence in the international arena, it is important to do that. And I am very much convinced that Japan will be able to do so. For that purpose, private sectors and the public sector and the citizens will have to work hand in hand together. So all Japan approach here is needed. That's how we are able to survive. I spoke longer than expected, assigned. So with this, I'd like to close my presentation. Thank you very much for your attention.
Thank you, Dr. Koyama. Next, we have a presentation from Dr. Shinichi Ishida, Deputy Director of the Rokkasho Fusion Institute, QST. He's going to talk about the research frontiers of fusion reactors and industrial application potential. Dr. Ishida, please. Thank you for the introduction. I'm Ishida from the Rokkasho Fusion Institute. Very honored to have this kind of opportunity today. Going to talk about the Rokkasho Fusion Institute activities and also talk about the research frontiers of fusion reactors and the potential for industrial applications of the technologies that come out of this facility. And I'm going to explain, and also we'll hear from the leading researchers and industry partners who are collaborating with us. This background photo is the aerial view of the Rokkasho Fusion Institute in Rokkasho Village, Aomori Prefecture. You see the arrow showing where the institute is. So that's where we are conducting our activities. So as have been mentioned, toward achieving the Paris Agreement goals, we're working on decarbonization and a carbon neutral society, and there's heightened activity toward that. And toward achieving those Paris Agreement goals, well, we analyzed what are the conditions that the nuclear fusion can play a role. We have developed various scenarios in terms of CO2 suppression. And so you see horizontal axis in terms of years. And with the acceleration of the low-carbon society, it is clear that we're going to need new power generation technologies to make up for the loss of others. And if nuclear fusion is going to be introduced into the market in the latter part of the 21st century, it will be able to play a major role. So nuclear fusion power generation process, well, there's this donut-shaped part in the middle, and there will be a plasma of 700 million degrees, and deuterium and tritium collide with each other at high speed, and they're converted into helium and fast neutrons. In this process, a lot of energy is generated. So 1 gram of fuel will generate energy equivalent to 8 tons of oil. And it's very environmentally friendly energy source, doesn't emit any CO2. And if fuel injection is stopped, reaction stops immediately, so it's a safe energy source. Also, the fuel, tritium, can be produced in the fusion reactors using lithium and beryllium. And the lithium and beryllium are widely abundant in the oceans, whereas deuterium and lithium are abundant in the oceans, beryllium abundant on land. And the blanket, so neutron made by the plasma comes in and hits beryllium, and it breeds into two, and it reacts with lithium, and the fuel tritium is generated. So the blanket is a very important part of this device, and so this shows the roadmap toward the demo plant. At the Naka Institute, we have the JT60, and so based on that, we have the ITER, and we're going to demonstrate the fusion burning, and we're going to then go to the demo reactor to demonstrate the power generation. And the ITER project, or in parallel to the ITER project, we have the broader approach activities to develop a wide range of approaches to support ITER and solve technical issues toward the demo. And that's done between Japan and Europe. At the Rokkasho Fusion Institute in Rokkasho Village, we have 2 projects. One is the International Fusion Energy Research Center, IFAC, and demo reactor design, theoretical simulation using supercomputers, and remote experience with ITER are conducted. And also, we have the largest accelerator development for the EVIDA business. And then ITER test blanket module project, and also AFNS fusion neutron source project. I'll explain about this later. So in the first part of my talk, I will present on the frontier of research and development towards the fusion demo reactor. So the demo reactor design is a key project of the Rokkasho Institute. And Mr. Yabuchi talked about this. Mr. Iwabuchi talked about this. So there's a joint special team for demo design established at the Rokkasho Institute. And you see in the map, many universities and research institutes and industry partners are participating, more than 100 participating now. So we've established this kind of a team and working on design. At this point, concerning the conceptual design of the demo plant, we have the chief researcher, Dr. Hiwatari. In the R&D of the demo reactor at the Rokkasho Fusion Institute, we're conducting conceptual design study. Here we determine the core performance of the demo reactor and determine the specifications and shapes of the main components such as vacuum vessel, superconducting coils, blanket, and diverter. So then next, I'd like to talk about the assembly procedure of the demo reactor and the overall configuration of the system. Well, first we assemble the vacuum vessel and the TF coil. TF coil is installed and the in-vessel components are assembled. Insert the inner blanket first. 2 segments. Next, insert the outer blankets. 3 segments. Finally, insert the diverter segment. So 3 segments are inserted. This process is repeated to complete the installation of the in-vessel components. Next step is to install the components outside of the vessel. In addition, steam generators and turbines will be installed. Finally, each building at the demo site is completed. So that's the overall configuration of the facility. So based on the technological foundations of ITER, we incorporate the plant technology and operation experience of industry. We draw up a feasible assembly plan and overall picture of the plant equipment, and based on that, we're able to evaluate the net electric power to be 250,000 kilowatt. So we were able to clarify the basic concept of the Japanese fusion demo plant for the first time, and we made an announcement last year. And you see the power distribution, and there's still a lot of power that's circulating within the plant. That means being consumed in the plant. So we need to improve on that. But based on this direction, we would like to further improve on the conceptual design of the demo plant. So the major technical challenges for the demo reactor will be the R&D of the blanket to extract fusion energy. In blanket development, there are 2 major issues. One is on the left, that is the ability to generate thermal energy and the fuel in the reactor. So we must demonstrate that fast neutrons heat cooling water, and also the neutrons, they are bred by beryllium, and they form reaction of neutrons and lithium to increase tritium fuel. And so we are planning to bring the blanket specimen. That's the ITER TBM experiment. So we're conducting that testing. The other is to learn the durability of the blanket enclosure. So the neutrons hit the structural material of the blanket and can cause it to become brittle, or could change to another element and generate helium. So we're testing the durability of the material. So we are simulating the neutron in the demonstration plant. So we need a neutron source, and so we're using a high current accelerator to simulate the fast neutron irradiation. So this is AFNS project. I will explain in more detail later. So test blanket module situation here. So as shown in the schedule, 2025 first plasma in ITER, in 2035 ITER start of operations of nuclear fusion. That's the schedule, and based on that, a blanket module necessary for each phase is being made. So with Unit 1, we check the mechanical characteristics. Unit 2, we look at the blanket functions, and we're preparing to do so. What we have written here is ITER tests the blanket module, which is a unique design by Japan. And you see a number of cylindrical modules containing lithium and beryllium. So as Mr. Iwabuchi said, this is one of the 4, and this was successful. And so blanket modules to be made by other members, well, we're going to be competing with them, so we really have to make good use of them. And so before bringing the blanket to ITER, we need to do safety testing. And so we are fabricating the engineering facility. So this shows the engineering test building. Started construction in March and July, August, November. So steadily it's progressing, and next week it's expected to be completed.
This is the aerial view of the Rokkasho Fusion Institute. In the upper right is a blanket engineering test building currently under construction. In addition, from left-hand side, from the top, there is the demo R&D, the collaborative research building, the computer and remote experiments building for supercomputers, administration, and the R&D, the research building for ITER remote experiments. And also we have IFMI, the EVIDA development and test building. Now for the second task, verification of the blanket material. It is necessary to test the durability of the blanket material by continuously exposing it to a large number of neutrons at high speed to simulate a fusion reaction. However, the energy of neutrons in existing nuclear reactors is too low, and the amount of neutrons in existing accelerator-based neutron sources is completely insufficient. Even the ITER itself is insufficient at this moment for pulsed operation. Therefore, a high-intensity neutron source that can be operated continuously is required. So you see the schematic chart. Specifically, as shown in the figure, the ions are accelerated in the high current accelerator and applied to a stream of liquid lithium to produce fast neutrons that are used for material irradiation. As you can see from the diagram on the right of the current and energy, the 125 milliampere, the continuous operation are needed. So in the world, we don't have this kind of the system. The x-axis shows the ion beam, and y-axis shows the average, the milliampere or the current, and then you see the huge difference here. So the kind of as you can see, the current and energy, the beam current much larger than that of conventional accelerators are required. Therefore, a fusion neutron source capable of producing such intense neutrons was named AFNS, and a conceptual design was carried out reflecting on the results of accelerator development and lithium target development obtained in the project that is being promoted in cooperation between Japan and Europe. And this is called IFMIF, EVIDA. So one of the features of this facility is that the neutrons produced by this neutron source can be applied not only to nuclear fusion, but also to other neutron applications, such as the production of RIs for medical use. So this is the accelerator part, which is playing the major role. In order to realize that, at this moment, within the IFMIF, the IVIDA project, we have linear and FA prototype accelerator is taken care of. So the Japan-Europe, the joint development is now taking place, and the demonstration is now about to be done. So I'd like to explain how we are working on the demonstration experiment. In last year, in January, we succeeded in accelerating neutron beams up to 5 MeV using the RFQ, a radio frequency quadruple accelerator and a beam dump for pulses. And currently, we are preparing for continuous operation at 5 MeV by installing a beam transport section and a beam dump for continuous operation. From next year onward, we will add a superconduction radio frequency accelerator, SRF, in place of the beam transport section and conduct the targeted 9 mega electron volt experiments. Let me explain to you what took place last year. Last July, we succeeded in accelerating deuterons to 5 MeV, 125 milliampere, using the world's largest 8-line RFQ. So the spec is 5 MeV, 125 mA. We were able to have a successful completion. Now that we have successfully accelerated impulses, we will replace the beam dump and finally try continuous operation next year. Now I'd like to give the microphone to Dr. Kondo, the group leader, who has been leading the demonstration experiment of the IFMIF prototype accelerator. We are collaborating with Europe on the research and development of neutron sources for material testing of fusion reactors. This neutron source requires a very powerful accelerator that can accelerate the world's largest power maximum current. We have successfully accelerated a pulse beam with the world's largest current. We are now working towards the success of steady-state acceleration. Here is a view of the accelerator room. You are able to see the accelerator room. There is an ion field in a square cage in the back, and then deuterium is accelerated to 5 MeV in the world's longest RFQ, which is made of copper and is 9.8 meters long. With this RFQ, we succeeded in accelerating a pulse beam with the world's largest current of 125 mA last July. This is newly constructed beam transport system for the test up to the steady-state beam. Since the development of the prototype accelerator is being carried out in cooperation between Japan and Europe, it will be important to immediately share the data not only with the Rokasho lab, the members, but also with researchers in Europe. For this purpose, the technology developed at the ITER Remote Experimentation Center will be used to enable remote participation from Europe. So we are able to share that information real time. This kind of technology, as has been explained earlier, is now deployed under the impact of COVID-19. And we have to say that the overseas engineers and technicians have difficulty coming over to Japan and also vice versa. So at this point, we'd like to ask the Deputy Director Hasegawa to take the floor. The system sends data measured by the IFMIF prototype accelerator, LIPAC, to Europe, and it was developed to share data and conduct experiments with researchers in Europe. So I led a task force to develop this system as a leader. And we succeeded in transferring the data from Rokasho to Fusion for energy, the fusion energy in Germany. Fusion for energy in Germany. Next, we'd like to share with you the situation of the data transfer. This is the LIPAC remote experiment room in the REC building. We have built a system that can transfer experimental data to Europe in almost real time. Operation test of the injector was carried out. This will allow us to communicate and collaborate on experiments even in remote areas. By integrating these fusion information infrastructure technologies, we envision a future fusion information science center. So we have the supercomputer JFIRST-1 or Luxus-2. We utilize these semiconductors in the supercomputers in operation to calculate plasma predictions. And when the remote experiments get started, we will work closely with domestic researchers and students who will participate in the ITER experiment in France. The vast amount of data generated by ITER, 100 petabytes, or the equivalent of 3 billion electronic books, will be stored in the data center and analyzed using AI and other techniques. And we would like to centralize these activities under the Fusion Information Science Center and use them for the design of future demo reactors. That's how we are looking at it.
So we work on supercomputers and we do design of the demo plant. And there's going to be JT60SA at the NACA lab. And we're going to collaborate also between industry and academia for R&D in optical digital technologies. In November, cooperative or cooperation agreement was signed between NTT and QST to develop innovative network technologies and create new nuclear fusion fields. So there is the need for real-time collection and analysis of huge amount of data in nuclear fusion. And so we would like to develop this into control technologies and plasma prediction systems. So jointly those will be developed with our partner. So here I talk about the second half of my talk. So various technologies developed, how to apply that in the industry. 4 points I want to touch upon. This is the first of the 4. So lithium, necessary to generate fuel in the blanket. So there's technology to have lithium permeate from seawater, and this is called LISMIC, lithium separation method by ionic conductor. So you have the ion conductor and the seawater and the pure water, and you apply voltage, and only the lithium will pass. So that's the gist of this technology. And on the surface, you do lithium adsorption, and then you have 850 times more lithium that passes. So that was a breakthrough. So we can now move from basic research to the pilot plant stage. So there is heightened demand for lithium batteries for electric vehicles. And based on lithium demand projections made in Japan, at around 2030, there's going to be deterioration of balance of supply and demand of lithium. So need for lithium recovery from used lithium batteries is rising. So in order to contribute to decarbonize society, we like to apply LISMIC not only to seawater, but also to lithium batteries and lithium recovery from brine in salt lakes in South America to speed up the social implementation of lithium recovery. So we have on the next slide the senior researcher Hoshino heading the lithium recovery to give you the outline of this effort. Here we are conducting R&D on the recovery of lithium from seawater, which is necessary for the production of nuclear fusion fuel. The key point is the membrane used to recover it from seawater, and the world's first technology to use an ion conductor is being used as a material for next-generation lithium-ion batteries as a membrane to recover it from seawater. So lithium recovery experiment, how is it being conducted? That is shown here. So this is the ion conductor that separates the lithium. Place the ion conductor on top of the electrode, and then electrodes are placed on top of that and devices are assembled. This equipment configuration is the world's first lithium recovery system. So you pass the lithium-containing solution, recovery solution, and pure water through the device, and the carbon dioxide gas is sprayed on the solution that is collected. When sprayed, white precipitate is produced. This white powder becomes lithium carbonate, the raw material for lithium-ion batteries. So in order to accelerate the commercialization of lithium recovery, we're conducting two research projects. One is this evaluating the recycling cost of spent lithium batteries. So there is this alliance with Idemitsu, Dowa Ecosystems, and Nichia. So QST Alliance has been formed with them, and JOGMEC Commission Research Project is being conducted at this alliance. So up until now, the ion conductor used was just one, but now we build a system with 20 ion conductors so that it can be demonstrated at several kilograms per year scale to evaluate the cost. The second is the JST START project. So we're developing lithium recovery technology from brine water in salt lakes. So there's been South American salt lakes, and they were drying in the sun. It took years, and productivity was low. And so that led to the projection that the supply could not keep up with demand. So apply the LISMIC method to brine of salt lakes for lithium recovery. That's the research being conducted. And so taking the outcome of this, we work with UMI, and we want to establish a lithium recovery venture in the future and conducting research towards that goal. So let's hear about this lithium recovery technology, industry partner, Idemitsu Kosan Company. So we have a message from Mr. Katsumata of Idemitsu. Hello, I'm Katsumata from Idemitsu Kosan. Our company is developing solid electrolytes for all solid-state lithium-ion batteries, which are promising next-generation batteries for the coming electrified society, represented by electric vehicles. From that angle, we are participating and cooperating as an alliance member for the social implementation of lithium recovery technology developed by QST under the theme of lithium recycling through lithium-ion battery recycling. I have high expectations for QST's fusion power generation as a future zero-emission energy source, and the lithium recovery technology was born as a spillover from fusion research. I hope that the results of the basic research on lithium recovery, which we are jointly working on, will contribute to the recovery technology of lithium isotopes, which are necessary for nuclear fusion and lead to the development of nuclear fusion. Thank you for your attention. So next, talk about securing beryllium resources. So we need 300 tons for the nuclear fusion reactor. And based on the survey of beryllium resources, there's abundant resources around the world. And so it has high melting temperature, very stable, and very strong and light. But we only have 300 tons production per annum, and the U.S. Dominates with 90% of market share, so the cost does not drop. So for the future construction of nuclear fusion reactors, we are developing, and we deem it's necessary to have a strategy to procure from other countries like Brazil. And so we have been working to create a cost-effective refining technology to secure a stable supply of beryllium. So the conventional refining process for beryllium, that's on the left-hand side, you see you need dissolution at 2000 degrees C, and there's a lot of processes where beryllium is in particulate form, which could be hazardous, and that led to higher cost. So in order to solve these issues at QST, we combine microwave heating and chemical treatment to dissolve beryllium ores. Applying this technology, as you can see, the heat treatment can be very low, 250 degrees, about half the number of processes, 1/100th energy use, and several hundredths size of plant, and not much of particle process, so better safety as well. So it's an innovative refinery technology with great economy and safety, and we made the press release last year, and we have great news. On the 15th of December, last week, has been adopted for the JST Research Collaboration Support Program. So together with Tohoku University and International Resource Development Research Center and Gaishi, we're working to establish industry academia collaborative center. So I call upon Mr. Nakamichi, who has led the project as the group leader. What we have developed is a new low-temperature purification technology for beryllium. Conventional beryllium refining technology required extremely high temperature of 2000 degrees Celsius and has a complicated process. This time, by combining microwave heating and a chemical treatment, we succeeded in refining at a very low temperature of less than 250 degrees Celsius. And this technology can be applied not only to beryllium, but also to various polymetallic clusters and the recycling of metals. So how to dissolve the beryllium ore is explained. This is beryllium ore, called beryl. It's also the source stone for emerald and aquamarine. The first step is to put this beryl through a grinder to make it finer. Next, a solution of alkali or acid is added for chemical treatment and microwave heating. And we can have full dissolution of beryllium from the ore through this process.
Until now, as can be seen here on the screen, the cycle has been to import beryllium from the United States and commercialize it. That has been the process. If the new technology is put to practical use, it will be possible to import various ores containing beryllium, refine them domestically, and supply raw materials as an energy-saving refining technology. That's a new route that we can think of. In addition, it is expected to supply raw materials through metal smelting formulation mines or the urban mines, in which we are able to utilize recycling from the used materials or used appliances. And we hope to contribute to the realization of the sustainable resource recycling society. Now at this moment, I'd like to introduce Mr. Ota, who has given us a message from the Nippon Gaishi, who has been collaborating with us. My name is Ota. I am in charge of beryllium application development at NGK. I'd like to talk about the industrial application of the metal refining technology developed by QST. I would also like to mention just two expectations from the corporate side. The first is that it is expected to be a new resource. Last year, we celebrated the 100th anniversary of our company's founding, and we are very grateful for the support we have received from our customers in using beryllium. We have been able to continue our business for over 60 years. Maintaining the quality, low cost, and stable procurement of beryllium material has been the key to success. It has been our biggest challenge since the beginning of our operation, and we have been working hard to improve the beryllium. I feel that the beryllium refining has a great promise. The second expectation is to save energy in the production process, specifically energy saving in the melting process during metal refining. This microwave dissolution method saves energy by lowering the temperature, and we expect that this will contribute to CO2 reduction. That's all. Thank you very much for your attention. Then the third case, the appropriate handling of tritium produced in the blanket is a key to ensuring the safety of the facility, preventing hydrogen explosion disasters from happening. This gaseous tritium needs to be catalytically oxidized and trapped as water in the fusion facility. However, one weakness of conventional catalyst is that the catalyst, generally precious metal particle such as platinum, is gradually coated with water vapor, and the catalytic reaction gradually decreases, so heating is essential to remove the vapor layer. Therefore, we took on the challenge to develop hydrophobic catalysts using inorganic materials that are heat resistant, flame resistant, and radiation resistant. Noting that hydrophobization reduces the contact area of the catalyst surface with water, we succeeded in hydrophobizing an inorganic catalyst support, here silica, by applying a silane treatment that bonds inorganic and organic materials. I would like to introduce the group leader, Dr. Iwai, to speak about the overview of this process. To remove tritium, it is necessary to turn it into water vapor by the use of tritium catalyst to oxidize it. Conventional catalysts for oxidizing tritiums are not effective in the presence of water vapor. A film of water covers the surface of the catalyst, causing the disadvantage that the oxidation of tritium could not be sustained. To deal with this issue, we have developed a new hydrophobic catalyst. This catalyst is chemically modified on the catalyst surface, making it difficult for water to stick to it. Next, the catalyst. Let me explain to you. Let the leader to explain to you how the inorganic materials with the is done. The catalysts are made from inorganic materials with the fine holes. First step is to attach platinum-containing agent that has catalytic capabilities to the inorganic materials. By penetration, the platinum is evenly adhered to the inorganic materials. The catalyst is then produced by evaporating the chemical and reducing it with hydrogen gas. The function is determined by the size of the particles, and so evaluation is done with a dedicated device. Thus, we were able to realize a new catalyst production method with the introduction of hydrophobicity into the inorganic materials. And we have been working with Tanaka Kikinzok. We were able to commercialize it, as can be seen on the right-hand side. In addition, this technology received the Catalyst Industry Association Technology Award this year, which is given to advanced technologies related to catalysts. From now on, we will use this to make a contribution to the hydrogen energy society. This can be applied to general industry and nuclear field as well. We hope to extend the product lineup by optimizing the manufacturing method for each application. So, starting with the prevention of the explosion, we were able to have the deployment for the general industry and also for the nuclear power generation. So this way, we are able to expand the scope of the product lineup. And this is the final case. Well, this is about the potential. I mentioned that AFNS is aiming at the fusion neutron source that is compatible with industrial applications of neutrons, and I will give you some concrete examples. So, as I just said, I would like to explain to you how this could be used in the industrial arena. Almost all of Japan's medical RIs are imported from overseas, so establishing a stable supply through domestic production has been an issue. In particular, the stable supply of molybdenum-99 and its parent, the nuclide, the stable supply of technetium-99, and its parent nuclide molybdenum-99 used in the nuclear medicine diagnosis is 100% imported. We also consider the use of AFNS for semiconductors and tracers for plant breeding and neutron radiographies applications. We hope that these applications will lead to the creation of new neutron applications and also industrial infrastructures. So we would like to make sure that all these applications can be taken care of in AFNS. So this way, we are able to establish the basic and foundation for the new industries. Let me go back to the aerial view of the Rokkasho Fusion Institute that I showed you at the beginning of this report. The AFNS will be constructed next to the Rokkasho Institute. That means the neutron utilization facilities will be clustered around the AFNS, forming a neutron forest. That's how we would term it. That's our expectation. We also hope that this will lead to the creation of a new neutron industrial base, expanding its scope to the surrounding areas. I hope that the new technologies introduced today will lead to the creation of the foundation for new industries. I hope that new technologies introduced today, such as lithium refining and battery recycling, the metal refining and others, will be conducive to the realization of the new industrial base for fusion. That's all for me. Thank you very much.
Thank you, Dr. Ishida. That concludes all of the presentations. Ladies and gentlemen, thank you very much for joining us for this annual symposium on the ITER project and BA activities. Finally, I'd like to ask Professor Junji Io, Chairman of the Organizing Committee of the Symposium, to deliver the closing remarks on behalf of the organizer. Professor Io, please. This is Io. Ladies and gentlemen, thank you. And I want to say a few words in closing on behalf of the organizer of the symposium. So COVID infection is expanding in Tokyo, but nevertheless, we had more than 180 people joining us in this hall. We thank you for your attendance. And also, we're simultaneously broadcasting on the internet. According to the Secretariat, we had as many as 300 people joining us and watching the live streaming. So this live streaming is something that we had been discussing for some time, but there was some reluctance because of intellectual property rights issues. But with this COVID, well, Dr. Koyama talked about a change in society, and so we decided to go ahead with this. And we had more than 12 people listening on the English channel as well. And on the Japanese channel, we have, well, there was the exchange of views with the young researchers and the industry. And many who participated in that session continued to listen in on this symposium. This symposium is held annually. So we start a new fiscal year in April. And as of April this year, because of COVID, we were not sure whether we could actually hold this symposium. And the organizing committee was established finally in July. At that time, we decided that we could hold this if we limit the number of attendees to about half of capacity. So at the Kadarashi ITER site, we heard about the vacuum vessels and sectors arriving and being assembled, and we could see that visually that there is progress being made. And also JT60SA has been completed. Regrettably, because of COVID, first plasma could not be achieved by today, but there is commissioning operation started, and that is also very encouraging. So nuclear fusion energy is the energy for the 21st century. So there's been high expectation for a long time, but regrettably, toward the goal of carbon neutrality in 2050, this may not arrive in time for that. So we had a special lecture by Dr. Koyama, talked about this new scenario of global change. And he presented various keywords that help us in our future thinking. And so the demo reactor beyond ITER is something that we would like to start thinking about. So in organizing this symposium, the QST staff were instrumental, and especially, well, in order to prevent the COVID spread, they disinfected this podium every time a speaker changed, and they also exchanged the microphone. So that was a lot of work by the people. And also we could not make a cloak available, but we're able to conclude this successfully. And I ask for your continued support and guidance. Professor Io, thank you so much. And I apologize for my inexperience in moderation, but I do thank you for staying with us till the end in this long symposium. With that, we'd like to conclude the symposium on the ITER project and the BA activities. Thank you so much. In order to avoid congestion,